the country would love to have a place like this where industry comes in, sponsors projects, and our students deliver the real solutions to real problems. And you got it, and you have this, and I'm also very grateful to all the parents who are here, who are supporting, and families who are supporting, and friends who are supporting their friends. Yes, there you go. And here, and we're all here to learn and enjoy and see what the students have been up to this whole year and how much they have learned and what they have contributed to their confidence company. My name is Theodora Schumann. I'm the coordinator of mechanical engineering projects. But in this session today, we will have two mechanical and one electrical and computer engineering project. And then throughout the afternoon, we will have mechanical and electrical in this room. And so now I want to introduce Dr. Shen Ren, who will introduce the teams and will be the moderator right now.
Hi everyone, I'm Shen. I'm the moderator for the session. So 3 teams, each team get 15 minutes presentation, and we'll coordinate about 5 minutes on Q&A. So if you have any questions or any comments, suggested feedback you want to give the team, that's the time to load it up, or just cheer up for the team. They really work hard for the past 1 year. And I serve as an advisor, but most of the time I feel like I'm more like a cheerleader or shepherd. That's all where I position myself. But today is maybe just a big party celebrating the hard work in the past 1 year. So first team is from mechanical engineering, and we have the sponsor from the Kenworth. Yours.
Alrighty, hello everyone. We are ME 26.3, and our project is the Kenworth T680 drag reduction system. And our faculty advisor is Dr. Ren, and our corporate sponsors are Maria Lowe's, Ryan Reed, and Scott Temple. All right, my name is Giselle.
I'm Karin.
I'm Kobe.
I'm Joseph.
Oh, and Connor's over there for emotional support. He broke his jaw, so he can't speak.
All right, so for those of you that don't know, Kenworth is North America's leading manufacturer for heavy-duty commercial trucks. These trucks are used for long-haul freight transportation, and they include aerodynamic features that help save significant amounts on operation and fuel costs. All right, so this leads us into our project goals. Kenworth has tasked us to actuate these panels highlighted in blue. They are our air dam and lower fairing extensions. In these images, you can see the deployed and stowed states. It's important to maintain a stowed state to avoid obstacles such as ramps, curbs, and turning on tight corners. And this is important because they could potentially tear off. And it's important to maintain a deployed state at highway speeds because it increases aerodynamic efficiency by 4%, which may seem small, but is significant when these trucks drive hundreds of thousands of miles in their lifetime. In our project outline, we'll be going over the project description and the requirements, the design methodology and solution, the manufacturing process, the testing results, and our conclusion.
All right, so to kickstart our design solutions, we have the lower fairing extensions, or LFEs for short. They are these little... Oh, thank you. Thank you. So we have the LFEs for short. What they are these little black panels that are denoted in the red box. And so now every time I say LFE, we all know what I'm talking about. So for the design constraints, Kenworth gave us, we needed to make it 8 inches below the fairing when it's deployed. So that yellow dotted line, we had to bring that down to the white dotted line. And when it's stowed, we had to do the same thing, except for now it could only be 2 inches. So how did we do that? So behind our design methodology, basically, we decided that the best way to tackle this problem would be to fold the LFEs under the truck. We would also be adding these extra inches to these already made LFEs. So the 8 inches would just be on the LFE, and all we would have to do is find a way to stow and deploy them. So how are we going to do this? We're actually going to tap into the air tanks that are already on the trucks. So you can think of the air tank as just an air compressor, and all it does is something that can pump up your tires or fill up a basketball. We want to tap into the system utilizing these pneumatic cylinders. And so basically what we're going to do is we're going to put air into that hole there, and what that'll cause is this skinny rod at the end to actually push out. So now we need a way to define this folding motion, but also actuate it via this pushing motion. So we've come up with the cylindrical slot. Basically, what it is, it's 3 separate parts. So we have the pins, the inner barrel, and the outer cylinder. The pins attach to this inner barrel and then are placed in this outer cylinder. But on this outer cylinder, all that it is are slots that are grooved into the outside, allowing the pins to be guided along. And all that this happens is it makes it so that we can make this pushing motion into a folding motion. Just like that. And then we're going to add these to these 2 parts of the truck. So in full motion, this is what our system looks like. Here we have a deployed and a stowed state. And basically what it is we're going to be using 8 cylindrical slots in total and 4 pneumatic cylinders. And we're going to put it on like this. So in order to talk about this in its entirety, we have to split this up into 2 separate sections. So let's start with the fronts. So here we have the fronts. Basically, the only difference between the fronts and the rears when designing was the brackets and how we were going to attach everything on the truck. And so what we did was we modded up these brackets, and we're going to utilize U-bolts and attach our pneumatic cylinders and our cylindrical slots, just like this. And then to attach it to the truck, basically all we're going to do is utilize 6 M6 bolts and attach it straight to the underside. That way you can take it on and off without much hassle. And so the rears work a lot like the fronts, except for the skeleton is a little bit different, so our mounting bracket had to be different. We'd still be utilizing those U-bolts, same attachment points, except for now we use 7 M6 bolts. We'll attach just like this. And so for our manufacturing process, we had a 3-step plan that we came up to be tried and true with. And so we spent a lot of time modeling the system. We spent a lot of time in CAD trying to figure out how to get the slots right and get everything kind of perfect. That way we could measure 18 times, cut once. That was the goal. And so after that, we decided to make the parts. And so what we did was we actually made it out of a sheet metal. And so we sent our parts off to Kenworth. And what they would do is they would laser cut these grooves and all these slots and then the overall shape. And they would put it into this machine. And so on that dotted line up top, what they would do is in this machine, it would actually be a folding line. And so all you'd have to do is make a 90-degree bend or however much you wanted it to go, and it would make our part. So after we made them, we then installed them. So here's our first rendition of it putting on the truck. The only difference we had to make from the actual modeling process to the installing process was make the slots a little bit longer. That way we could add a little bit more adjustability in our design. And so when we move on to the testing results, here we have an outside view, and so this is actually what our system does. Yeah, thank you. And so it folds out and it folds in, and if you want to see the inside view and see all of our handiwork, here it is too. Yeah, thank you. And if you didn't have enough of that, here's the back. So it works a lot of the same way. So there you go. Yeah, and then one more. Oh, yeah. So our design worked as tested. We were actually very proud with what we got to come up with.
All right, now let's talk about the air dam, which exists specifically in this region of the truck and is referring to the components below the front bumper. Kenworth has tasked us with creating a system that extends down 7 inches below the lowest point on the front bumper when deployed, and retracts to at most 2 inches below the lowest point on the front bumper when stowed. We have opted to go for a folding panel design methodology. So we have 2 panels, our inner and outer dynamic panels, which fold up and in when stowed and down and out when deployed. And this is what the system looks like as a 3D model. Something you may notice about this is it's only half of a system due to the mirror symmetry of the truck that we were working on. We only needed to design half a system to get a whole idea. We split this assembly into 3 sub-assemblies. So starting with our intermediary panels, these serve as the connection point between the underside of the truck and our dynamic panels, which are the ones doing the folding. Our final subassembly is our actuation subassembly. This is made up of our mounting bracket, which similarly attaches to the underside of the truck and is connected to our 2 spring retract air cylinders, which in turn are connected to our dynamic panels, allowing them to move with the presence of air. Thank you. We followed similar logic to the LFE for making this. We started off by spending a lot of time modeling, and then we sent our models off to Kenworth to have them laser cut those sheet metal parts and weld them together. And then finally, we installed them onto the truck. In terms of testing, our system functioned overall mostly as intended. We ran into some minor issues with overextension of our dynamic panels. This was due to an incorrect stroke length on our air cylinders. This caused some warping issues, which in turn led to some gaps in the system. But overall, it was fairly successful.
So up until this point, we've talked about the two physical components of our system, the air dam and the lower fairing extensions. But we need a way to connect these to the truck and actually operate them. So this is where the control system comes into play. The goal of the control system is to connect those two physical components to the truck computer and allow us to actuate the panels under the correct conditions. There are three main categories of constraints that we had in mind when designing the control system. Another way of thinking about this is when should our panels deploy? So the first category is speed. We know that we want our panels to deploy at highway speeds and stow below highway speeds. Kenworth has given us a threshold of 55 miles per hour. The second set of constraints are what I call the truck variables. So this is everything coming from different parts of the truck that will impact whether we're able to use our system. So a key example is the air tank pressure. Like Kobe mentioned, we're using pneumatic actuation, so we need a minimum pressure in order for our system to work. The last set has to do with our proximity sensors. We use these to give us feedback on what our panels are actually doing when we tell them to move. We designed the sensor system so that each dynamic panel would have two sets of sensors. The first set tells us when a panel is fully stowed. In this set, we put a sensor on the inner part of the truck and its magnet on the bottom of the panel. When the panel folds up into the stowed position, the magnet comes close to the sensor and sends a signal. The second set tells us whether the panel is fully deployed. We put a sensor on the outer part of the truck and its magnet on the top part of the panel. When the panel folds out into the deployed position, again, it sends a signal. If neither of the sensors send a signal, that tells us that the panel is stuck somewhere in between being fully deployed and fully stowed. In certain cases, this can indicate a critical error, like maybe the panel just came off the truck completely and that's why we're not getting any signals. I also want to note that we made some 3D printed extenders to help our sensors get close enough to their magnets. To plan out the logic of what happens when in our control system, we made a great big flowchart, but I've boiled it down to just the crucial components here. So first, the vehicle turns on. Then the driver can choose to initiate a systems check. And then we start driving. Then we're checking the vehicle factors that I mentioned on the constraint slide continuously. If we meet the right conditions, the panels will either deploy or stow. After we finished the flowchart, we implemented this logic in a truck industry standard control software. Ideally, to test our control system, we'd just put all of our systems onto the truck, get on a highway, and see what happens. But at this stage in prototyping, that's not safe to do. So instead, we used the same software that we used to implement our logic to do some simulations and test our software. I'll give you an example of what one of these tests looked like. Let's say we wanted to test whether we're deploying at the right times. I would set the speed to, say, 60 miles per hour, tell the sensors that they're all stowed, and set all our other variables to be as we expect. We run it and see that we did deploy the panels.
All right, so in conclusion, our air dam met the design requirements, and then our LFE also met the design requirements and the performance requirements. So for our future work, we would like another iteration to redesign some of the components in the air dam, as well as attaching a locking mechanism and potentially painting it. Also, the LFE weighs around 20 pounds right now, so we would like to change some of the materials to make the LFE lighter. And then for our control system, we would just like to optimize our timing. We want to acknowledge our sponsors. We want to thank you for helping us through this project. It was both valuable and very enjoyable for us students, and we learned a lot from you guys, and it's going to make us better engineers for the future. And thank you for listening. Do you guys have questions?
Any questions? I'm happy to pass around the microphone.
Was this the first time that this type of system was deployed on the trucks? It seemed like, what led them to do it now? Why wasn't it done, considered before?
This specific system, no, I don't believe they've used before. What made them consider using it is that they had already run the aerodynamic simulations that show us that that deploying the panels does give them greater efficiency. But they were hearing from their customers that truck drivers were taking the static panels off of their trucks because of the issues with running into obstacles.
Next question here.
What obstacles, if there were any, did y'all encounter when like programming and CADing the LFE?
In terms of the LFE and specifics, the only real obstacle we ran into was when we put them on the truck. So what we were utilizing was a spring retracted air cylinder, and so you'd push air in, take air out, and then a spring would basically close the entire system. And so the only thing we ran into was the spring wasn't strong enough to actually close the system. So we had to get an external spring and just put it on the system to help it along with that other spring force. And so that's kind of it.
Thanks for the presentation. You guys mentioned in the last slide that for future you want to look at the locking. Or is the locking for when you're folded the you're folding the LFE? Could you elaborate just a little bit more on what you're looking forward to do?
Yeah, so we were thinking of adding a locking mechanism for when the air dam specifically was deployed. Because there is so much force from the air on that system, we were worried that just the air pressure in our air cylinders would not be enough to overcome that.
Thanks for the presentation. Yeah, I was just wondering if you considered an all-electric system of actuators and did trade-offs between that and the pneumatic in your setup for the project.
So one of the things that we were aiming for with our final design was having a passive stow system. So I think we mentioned this in the presentation, but all of our air cylinders are spring retract. So if any of the systems on the truck were to fail in any way, they would just automatically retract, and we wouldn't have to worry about that.
Thanks.
Mm-hmm.
The last one.
Hi, thanks. Great presentation. I was wondering, did you have to factor in any weather? Because I know lots of times when you're out driving, there's huge gusts of wind and stuff like that.
Yes, great question. So we did consider that in our brainstorming phase of what we wanted to do, because there's going to be rain, snow, and water. So we wanted to make sure that our systems weren't going to corrode and that things weren't going to get stuck in there. So that's why we went with this design. We went through so many other iterations of designs where things could get stuck in there, and that's also why we chose to do pneumatic actuation, because if we used a motor, it could potentially corrode and things could get stuck in it. So that's kind of why we went this way. But yeah, we did consider that in our design. And great question. Thank you for asking.
Thank you, and thank you for the Kenworth for the opportunity.
Your things are wrong.
Are you the first one to speak?
I'm the first one.
You're the first one. Okay. Who's the second one?
So Dale's on that side.
Yeah, you're the one for each.
Testing, testing, testing. Testing.
All right, we have the next presentation also from mechanical engineering from the project furnishing.
Thank you. Hello, hello.
Hello, we are Project Furnish. We are ME 26.4. Our project is the One Pack, and our sponsor is Project Furnish.
My clicker. It was looking so promising. Little preview of the presentation you're about to see.
I'm Dorothy.
I'm Eric.
I'm Colin.
I'm Jet.
And I'm Mike.
Our sponsor is Phil Brock, and our advisors are Dr. Schumann and Dr. Gilbertson. So how many of you have more than one hiking backpack at home? So that's about a quarter of you. So when you go out hiking, you can go on trips for multiple lengths of time. So a week, a day. If you're going to Discovery Park up in northwest Seattle, you're only just going to go out for the day. So you won't need that much stuff, so you only need a small backpack like this. But if you're going to Mount Rainier, that's at least several days. And so you're going to be carrying a lot more stuff, and you'll need a much larger backpack like one of these. The problem with this is that long hikes take a lot more planning, and so you're less likely to do them than you would a smaller hike like a day hike. And so the larger backpacks will just be sitting in your closet most of the year and will only be used a few times. Plus, you'll be carrying a bunch of other stuff like a chair and a tent, so we thought, why not combine all of this gear into one? This is the task that our sponsor, Project Furnish, entrusted us with. Our backpack had to meet several criteria. First, it had to be configurable between 3 different volumes: a small size, a medium size, and a large size. Second, it had to have a detachable rigid metal frame that could transform into a camping chair that could hold up to 250 pounds. Third, the frame had to be able to transform into a structure for a single-person tent. Nothing like this had ever been done before, so until now there was nothing like this on the market.
With all that in mind, we developed the One Pack. This is a system that combines the functionality of a backpack that can hold a lot of volume with all the things that you would want to bring camping with you. Our team designed with an idea of making things multifunctional, so everything in this pack actually has 2 uses. When you buy a backpack in this day and age, it can really only do one thing: carry your stuff out with you when you're hiking. This pack as well can transform, so we take the pack into 3 different levels. Starting at our base level, this is a 10-liter fanny pack. This can exist without our frame or any of the other components within the bag, and is a soft piece of equipment that you can take anywhere with you on a hike, a small day hike, or something like a run. Going forward into something for a longer distance hike, this is a 30-liter pack. We integrate our rigid frame that can also hold 16 feet of tent poles and integrates our comfort system of straps and a back plate. This 20-liter that we add on to create a 30-liter bag actually unfolds into a tent footprint. So when you finish up your hike, you can make it to the top, build your tent, and set up your chair. Now in its full size, this is a 50-liter pack. This integrates 2 of those 20-liter sacks that we have developed, as well as everything else that transforms. This whole system is meant to go on a multiple-day hike and can support you through any sort of weather as this second 20-liter pack unfolds into a rain fly. With all of these three ways to do this in mind, we're going to show you the largest pack transforming into the actual camp. There's a quick video of Jet. And if you can believe it, she actually moves at this speed.
Normal jet speed.
It's pretty incredible. Thank you. So now that you've seen how it operates, we're going to get into the nitty-gritty details of the 3 main components of this bag: the frame, the fabrics, and the straps and padding.
Diving into the details of what separates our external frame from other packs on the market, 2 questions arise. Oh, Kobe, do you have a question? Why don't I buy an internal frame backpack? Well, our backpack exceeds internal frame backpacks because backpacks internally normally sit flush on your back and provide poor ventilation. Secondly, internal backpacks rarely ever detach modularly like ours do. Oh, do you have another question, Kobe? So why don't I buy a different external frame backpack? Why don't I buy a different external frame backpack? Great question. You're on fire today. I couldn't have said it better myself. Why I don't buy an external frame backpack? Our backpack not only is an external frame, but it also transforms, as mentioned, into a chair and houses tent poles. Moving forward, we have one of our first innovations on external frame backpacks, the shoulder and mesh height adjustability. So with our plastic printed joints, we are able to slide up and down the joints that your shoulders are sat on, as well as the back pad that your back rests on. Furthermore, the shoulder straps adjust in width by holes on the rib that allow wider people or narrow people to fit our backpack comfortably. Our second innovation is the tent pole housing.
Colin, where did the tent poles go?
Eric, splendid question. The tent poles actually hide within the vertical tubing of the backpack. What? Did we just do that? Yes, we did. Hashtag tent tech. Our third innovation, what really knocks it out of the park, is our frame's ability to turn into a chair. So with chair structures and joints fit within the frame, you are able to pull them out, rearrange them into where they belong to be into chair mode, and then get stuck in to the chair to turn it into a fully functioning camp chair. Hashtag chair tech. Moving on, I will pass on the mic to Jet to talk about the fabric system.
So because we wanted to have the dual usability of a lot of components of the tent. When we were researching for this, we were looking at how do you turn a backpack, like some component of a backpack, into a tent. And the only thing we really came up with that is how some ultralight backpackers will crawl into their backpack at the end of the night, bundle up in a heavy coat, and then fall asleep, which wasn't very accessible for everybody. And we wanted to do something different. So we started looking at it separately, or backwards, where we looked at how to turn components of a tent into the components of a backpack. For that, there still wasn't a lot of evidence or a lot of research around how one could actually do that. And so we got out a piece of paper, we marked on it the dimensions that we wanted to be able to fold it into, and we just folded it until we got some kind of compartment that was the right dimensions that we wanted. From there, we scaled it up to a fabric scale, or a fabric-based design to see how it would actually work. We tested a few different designs, and we tried different ways to connect the edges together with hook and loop fasteners, which the most common brand name is Velcro, cinching, and zippers. The design we ended up going forward with had the most accessibility and easily foldable and easy access to all the materials inside, and it has this dual cinching and zipping technique. We were able to use this design and put it on both the Rainfly and the footprint of the tent. This here is a video of the construction of the footprint of the tent into one of our containers. So the footprint of the tent goes under your tent when you make it, and it protects it from the rough surface on the ground. You fold up here. This little blue container I put in, it's a bear canister. A lot of hikers use it to keep their food safe from bears, but it's super difficult to fit inside most hiking backpacks without just like shoving it in weird, and then if you want to access your food, you have to kind of pull everything out of your backpack. So we kept in mind with that having a container that was easily accessible for, just front access. You don't have to dig through your back. The Rainfly also has the same rectangular section that folds into the actual bag itself. Here you see it being folded up. The Rainfly itself is a very three-dimensional system. It's not flat in its entirety. We were able, because there is a flat surface on it though, we are able to still have the same system work for anything that has a flat surface on it, even if the structure itself is not flat, which is very unique to our design. The chair fabric, we used it as a pack cover because when you have the Rainfly and the footprint, they're very susceptible to damage. Because they're what keep you dry at night, we wanted to have it protected. And for that, we have it be the pack cover because it can take a lot more damage that the other packs would not otherwise be able to take. And so if you're walking through brush or pokey branches, blackberries, whatever, it keeps it safe.
So moving on to the straps and padding, the reason why we wanted to focus on this part is it's simply because our backpack used an external frame, and also since we are making something that has never been on the market, we wanted not only to focus on the functionality, but also on the comfort and ventilation. So for this part, we focused on ventilation and comfort. Comfort, we wanted for the user to use it for a long time and still feel comfortable. And since everybody doesn't have the same comfort level, we give the options to the user to choose their comfort. And about ventilation, since having a larger backpack on your back can be sweaty and hot, so we wanted to make a space between the user's bag and the backpack, and with something that can help us to create that space. So digging deep into the parts of the design, we have the shoulder straps, back mesh, and the hip belt. The shoulder straps are adjustable on the frame, as my friend Colin was saying. And we have a back mesh, which is basically what's going to help us create that space in between the back of the user and the backpack so that air can flow through the back and keep them cooler. And we have a hip belt, which is basically our 10-liter and our fanny pack. And since we wanted to give the options to the user to choose their comfort, we've developed 3 padding options that we're going to see in the next one. We have the kidney, the circular, and the rectangular one. And all of them come in the same backpack so that you can try them all and see what is the most comfortable for you. And all of them, they give a different comfort level. So another thing is that the way that they go to the mesh is by Velcro, so that it can be easy to swap. So you have them, you try, whatever feels comfortable for you, and it's the one that you're going to keep.
All right, to come to a conclusion, our team was able to complete the challenge of generating this pack, a first of its kind. Nothing of it existed before, and we went from idea all the way to a fully functioning prototype. We met all of our deliverables and are here to show that to you all. Some future work to recommend to Project Furnish would be to do things like upscaling the way that manufacturing some of these parts would be, such as injection molding for some of the clamps and fasteners on this, as well as using things like carbon composites to replace metals within the pack to create a more rigid frame and a little bit lighter weight. We also would recommend using things such as recycled fabrics or upcycled gear to maintain a more sustainable production system. We want to express a big thank you to the Seattle University Project Center, as well as Jack and Romali, our machine shop leader, as well as our professors, Dr. Schumann and Dr. Gilbertson, for advising our team, and Phil from Project Furnish for sponsoring this project. Thank you.
Questions?
So, which one of you is going to be taking this out on summer camp, this summer to hike with and test it out?
We actually made 2 of these so Phil and his daughter can go camping this summer. So we're replacing his full backpacking gear list.
How heavy is each component of the system?
So, Colin, do you want to answer this?
We're going to find a scale, and we'll get back to you. Meet us in the main lobby in like 20 minutes. We don't know yet, but a main argument we have for its weight is that in comparison to an empty bag, maybe it's heavier, but in comparison to a bag that would have a tent packed in it and a chair packed in it, our argument is that our empty bag that can serve those purposes would be approximately the same weight as that, if that attempts to answer the question without saying the number.
I got one. So you said you used additive manufacturing or 3D printing to make the prototypes of the fittings for the joints. Did you happen? You did a lot of real creative design work here. Did you, sometimes with additive you can make things you can't do any other way. Did you come up with any bright ideas where you might be able to do something kind of innovative with additive manufacturing that you just simply couldn't make using normal manufacturing?
I'd say it's just a matter of, if we were to do additive manufacturing, finding something that's strong enough to support the weight and like fluctuations of weight that would occur when someone's sitting in the chair. I've probably sat in that chair like 40 times and it snapped 38. So, and I'm not fat, so. But yeah, it's just a matter of finding the filament or necessary means that would support that weight, because we've tried PLA, PC, nylon, all sorts of stuff, and it's just a matter of finding something that could support us.
Yeah, when you get to volume, I think injection molding for the brackets is going to be just right. But yeah, just thought you might have had some creative ideas of some other stuff you can do. Thanks. Nice job.
Oh, thanks, man.
Very good presentation, everybody. Lots of creative work here. I'm wondering how much of your work was informed by actual experience. So do any of you have camping experience that you might have been able to use in your design procedure?
I don't think actually any of us have gone formally backpacking, but a lot of us have done very camping adjacent activities. I think we all like to hike a lot. And our sponsor actually is Dr. Gilbertson. He's a world-renowned mountain climber, so we got a lot of expertise directly from him about what to change, what to make sure. One of the big things was make sure nothing comes off of the pack, because it's super easy to lose things when you're out, moving around. And if you lose a very crucial component of your bag, you either don't get home or your bag fails you. So, thank you for the question.
Thank you. Thank you so much. Where's the UCE team?
Yeah, supposedly. Supposed to be here?
Are you guys presenting? Do you have your laptop or you use a...
We're bringing our laptop.
Where's the laptop? Okay. Is that on your laptop?
Yeah, that's what we thought. See, they didn't have it, so that's why I had to bring my computer.
Yeah, I know. Yeah, we were waiting for you. Where'd you go?
Just in case, because I need a USB in case they need it.
Sure.
Wow, that was scary.
That was
what is this?
Are these things connected in here?
Yeah, no, it's connected. It's connected. So once... the clicker's connected? Share on Zoom and...
Well, we have a slide there already, but I don't know what this is. Audio console.
Hello. Oh, the mic is working. Mic 2.
All right. So where are we standing?
Should we just use this one? Wait, is it share on Zoom?
Yo no sé. Yo no comprendo. Tecnología.
One of you.
So where do we stand up? Oh, put on your own side.
Oh, thank you. Yeah, you're gonna go first.
So I think.
Oh no, is it Puna that gets introduced? No, okay, everybody else stand behind. Oh, is this connected?
John, put it in there. You have the worksheet? Oh, behind the
Presenting team for the
Next one.
session, and we have the electrical engineering and the sponsor from the Sound Transit.
Hello, everyone. We are ECE 26.2 Sound Transit Lighted Platform Birthday Marker, and we'll start off with some team introductions.
Hello, I'm Zachary. I'm an electrical engineering major.
Hi, my name is Amar. I'm a computer engineering major.
Hi, I'm Puna. I'm also an electrical engineering major.
Hi everyone, my name is John. I'm an electrical engineer major.
Hello, my name is Brandon, and I am a computer engineering student.
So let's meet our support team. First, we have our liaison engineer, Thompson Wang. He's a systems engineer of train control over at Sound Transit. And next, we have our faculty advisor, Dr. Shiny Abraham. And here's a brief overview of what we'll be discussing today. We'll start off with a sponsor introduction, move on to our project introduction, list out our specifications, go over our testing, show a demonstration video of our system and the results, show our budget for the system, and finally end with a Q&A session. Starting off with our sponsor, Sound Transit is the regional public transportation agency here in the Puget Sound. They operate several key transit services, such as the express buses, the commuter trains like the Sounder, and the Link Light Rail, which is a system we've been working with for the project. And altogether, Sound Transit plays a major role in moving people efficiently throughout the region. And here's some statistics from 2025, with the numbers on the top showing the number of passengers for the one line alone, and the numbers on the bottom showing the total number of passengers for all of Sound Transit systems. And Sound Transit's mission is focused on providing safe, reliable, and high-quality transit. They prioritize quality by ensuring efficient and well-maintained services. Safety is at the core operation to protect both the passengers and the staff. And Sound Transit emphasizes inclusion and respect, making transit accessible and welcoming for everyone in the community.
So now we'll introduce our project, starting with some brief terminology that we'll be using throughout this presentation. So for the light rail, there are multiple cars in one light rail train, and Sound Transit runs 2-car, 3-car, and 4-car train configurations. Next, the berthing markers here circled in red are static physical signs on the platforms to indicate to the train operator where they should stop the train. And finally, tactile wayfinding paths are these physical textured paths on each platform for those who are visually impaired to help them navigate around the station. So here's our problem statement. Currently, Sound Transit runs 2, 3, and 4-car train configurations with static berthing markers, which requires operators to rely on memory for selecting the correct stopping point for the train. And this reliance on human decision-making increases the risk of error. And the risk of error we're talking about can be visualized here in these two diagrams on the right. And so on the top diagram is an example of a 4-car train pulling to the static 4-car berthing marker in which there are no issues. There's also no issues with a 3-car train pulling, as we see the 2 tactile wayfinding paths align perfectly with the doors of cars 2 and cars 3. However, on the bottom diagram, we see an example of a 2-car train pulling into the station, and if it stops at this 4-car static berthing marker, we now have a situation where one of the paths, the left path, now leads to an area where there is no train, and therefore a drop-off into an empty track, and this is a safety hazard for those who are visually impaired. Aside from this safety hazard, we also have a situation where those who are waiting to board the train on the far left side may now have to run 2 car lengths to board the train, and this creates some operational inconsistencies for Sound Transit.
So now we're going to talk about some project constraints that was provided by our sponsor. We have 4. First one, on the very left side, we have that the team couldn't have access to the current Wi-Fi or cellular connection that Sound Transit has. Secondly, as we mentioned earlier, for our project statement, we were asked to reduce the human risk error, so we'll not be relying on any operator input for our solution. Thirdly, we're asked that we also don't have access to the current power outlet that Sound Transit has. So in order to power up our system, we'll be using batteries to make sure that our system runs fully. And lastly, we were asked that we'll come up with external product implementation. This is to make sure that we don't interfere with any current system that Sound Transit are operating.
So we're going to shift over and talk about our solution that we designed for this problem. And so we broke it up into 4 main components. We're going to use RFID technology as our detection method for counting the number of trains and therefore the length of train, or number of cars and the length of train. For our data communication, we are using MQTT data communication protocol and cellular connectivity. For our power supply, we are using rechargeable lithium-ion batteries. And finally, our LED sign serves as our lighted dynamic berthing marker for the train operator to know where to stop. So here's a functional block diagram of our solution. And if we start on the left, we're going to see our RFID system, in which we're going to have 1 RFID tag per train car. And so as a train passes an RFID reader on the track side, it's going to read the number of tags and therefore the number of cars on the train. This is hardwired to an ESP32 microcontroller, which will package and publish the data over MQTT protocol using AWS Cloud. And this is going to be sent to our other system on the station side, on the right side, which is going to be another ESP32 microcontroller that is going to receive the data upon a publish and use that data to command a lighted berthing marker.
So with these solution details in mind, here are 2 animations that show a bird's eye view of our proposed solution. One animation is for the southbound track, which is shown on the left, and one is shown as the northbound track, which is the animation on the right. Both of these train counting systems will work exactly the same, so we can just look at one animation to make it more simple. So looking at the left southbound animation, we can see that our car counting system starts with an RFID scanner placed approximately 700 feet away from the station. And this RFID scanner will scan the number of incoming cars that are tagged with an RFID tag. And this data will then be sent over cellular network to the platform side, where the LED berthing marker will see if a 2-car, 3-car, or 4-car train is approaching. If a 2-car train approaches, the LED berthing marker will turn on to indicate to operators where they should stop or berth when entering the station. This will allow the passengers to safely offload and load onto the train. And then once the train leaves, the LED berthing marker will shut off, which will allow the cycle to repeat itself for the next incoming light rail.
Moving on to the specifications. Starting off with the RFID system, the first specification is that our system must fully operate on battery power for at least 20 hours to cover the 19-hour workday from 5 a.m. to 12 a.m. And next, the next two specifications is that a system must reliably read tags that are simultaneously 10 feet away from the RFID scanner and also moving 32 miles per hour to match the real-world circumstances. And finally, is to ensure that a system has 100% read reliability, meaning that every tag that passes the RFID scanner is counted and detected only once to ensure the correct card length.
So for the MQTT specification, we have 5 criteria. The first 2 are the latency and accuracy. The third one is the elevation of testing environment. As we all know, the Soundtrans has different elevated stations, such as underground station of Capitol Hill to the above ground station of Northgate. So we want to make sure that our solution can fit to all environment that Soundtrans station has. And the last 2 are the startup cellular connect speed, as well as the transition from the primary to the backup server.
Moving on to the LED specifications. The first specification is that it must be the same height as the current 4-car berthing marker, which is about 10 feet. Moving on, it must be readable in all weather and time conditions. For our specific LED berthing marker, it is as bright as the headlights on a car, or 900 to 1200 lumens. Lastly, it must light up instantaneously upon receiving the message that a 2-car train is inbound.
Moving on to our testing. And our testing can be broken into 3 phases. The first one being the rough compilation of our system, the next being the speed verification, and finally full integration. Starting off with phase 1, the main goal of this phase was to test the functionality of each subcomponent. And with this, we were able to determine the required read power to match that 10-foot read distance. And we were also able to determine the data transmission time between the last tag being scanned on the train and the LED sign turning on. And finally, we were able to verify that the LED sign lights up when only 2 cars is scanned. For our phase 2 testing, the main goal was to check the speed reliability of the RFID scanner. And to do this, we placed a UHF RFID tag on 2 spike balls, and this is to simulate a 2-car train. And we threw these spike balls past the RFID scanner at 37 miles per hour, which covers the 32 mile per hour specification. And we were able to test this speed at the 10-foot optimal read distance. And for phase 3 testing, we were running our system in a real-world implementation. And to this, we placed a UHF RFID tag on 2 of our personal cars, again to simulate a 2-car train. And we drove past the RFID scanner at 35 miles per hour, which was the speed limit of the street. And we used an open street as the testing location to ensure the safety of others and ourselves. And we were able to check the accuracy of the RFID scanner system and the send and receive speed from the last tag being scanned to the LED sign turning on.
So throughout our different phases of testing, we encountered a variety of challenges, which can be broken up into software and hardware challenges. For the software side, the initial setup of the RFID chip as well as the microcontrollers was difficult because the Arduino libraries that we had used were out of date and poorly documented, specifically for the security measures that we wanted to implement. For the hardware side, we had issues with the external antenna for the RFID chip, as well as making a custom power management system with the LiPo batteries that were mentioned before. However, the most interesting challenge we encountered was detecting other RFID tags. In the phase 3 testing, as Hamar had mentioned, we had tagged 2 of our personal vehicles with RFID tags. However, through our testing, we actually found that we were scanning more tags than we had brought. And this is obviously impossible, but through deliberation, the team determined that it was likely because of other tags in the area in other cars. And this is feasible because systems like the Good2Go, as well as other tolling services, use the same UHF RFID technology that our team is using. So in order to combat this, our team has implemented a keyed tag system where each of our tags are encoded with a specific key that the scanner looks for first before actually counting it as a car. Now moving on to a demonstration video and the results of our phase 3 testing. Before we begin the video, I'd like to give a little bit of context for what you're about to watch. So we have our teammate that is standing next to our RFID scanner on the sidewalk, and we'll have 2 of our personal vehicles that are tagged with UHF RFID tags, and these tags were placed on the inside of the passenger side window of each of our vehicles. And these vehicles will be coming in towards the left side, which is shown here. And we were driving in such a way that the vehicles would be back-to-back to simulate a 2-car light rail coming into a station. And again, we were driving at 35 miles per hour. And lastly, the video is played at 0.75 times speed to make it easier for viewing. So if we begin the video here, we could see the first car pulling out from this side of the road and the second car following quite closely behind. And we're traveling at 35 miles per hour here. So the first car just passed the scanner. And so this means one car has been scanned by the system, and the second car just passed by the scanner, which means 2 cars are now scanned by the scanner. And with this information, the microcontroller determines that a 2-car train is approaching the station, and that data is then sent to the LED berthing marker. And as you can see, the LED berthing marker does turn on to indicate to operators that they should stop at that point. Now, moving on to the results of our phase 3 testing, we found that we either met or exceeded the previous specifications that were shown earlier, specifically for battery life, read range, and data transmission accuracy. However, for the time from the last car scan to when the LED berthing marker turns on, was a little bit over what we had anticipated. So our original specification was 8.5 seconds, which can be broken up into 3 different intervals. The first one is 5 seconds, and that is a timer that starts after the end of each car being scanned, and this is to allow any cars behind that one to be scanned during that interval. So once that time expires, then an additional 3 seconds is allocated for data transmission time, and then an additional ½ second is accounted for the LED berthing marker to turn on and interpret that. So we found that we were actually closer to 10 seconds in our latency. However, to account for this additional latency, the team has strategically recommended to place the RFID scanner further before the station platform to account for that time.
So moving on to the recommendation or the next step that if we would have, or the future steps. So the first one is that we want to transition from the lithium-ion battery to the power plug, and this is because to reduce the number of times that sound transit engineers need to replace. And the second one is a different condition test. And so due to the limited time, the team didn't test all the conditions. We did test some of the conditions, such as at the Capitol Hill station, underground garage, or even above ground stations. But we didn't test all the sound transit stations that we have, so that's one thing. And then secondly is to test all the weather environment, which includes heavy snow or heavy rains.
Moving on to the budget now. As you can see from this breakdown, this is the cost to deploy. This accounts for every item that we used within the final prototype of our project. As you can see from this breakdown, the 2 biggest contributors to the budget are the microcontrollers, which make up half of the overall budget, as well as the RFID tags and readers, which make up about a third of the budget, making the grand total for one track to be about $1,600. But as you saw from our animation, there are 2 tracks per station, which brings the ultimate total for one station to be about $3,200. Moving on to the lessons learned, these are lessons that we learned throughout our journey in this project, and these are lessons that we will take into our professional lives. For me specifically, I learned the lesson of working within a creative and environment that allowed more freedom of creativity.
The lesson that I learned was to know your peers outside of the academic space, which makes working with them easier.
Yeah, I learned how to create an inclusive and welcoming environment for all of our team members to feel like they can have a space where they can not only provide help, but ask for help and not be feeling judged.
For me, time management was crucial because I'm so used to working on projects that are 10 weeks long or 1 quarter, and this is a whole year. And so I think learning to spread that out.
Lastly, for me, something that I learned is that working with the real industries outside of Seattle U. So definitely this is something that we learned, such as specification, codes, and regulation, that we will never be encountered if we didn't work with Sound Transit. So that's the lesson that I learned. And so now we'd like to open the floor for the Q&A session. Thank you.
Questions?
Thank you. Did you ever figure out why your timing didn't work out? Why you were 10 seconds instead of 8.5 seconds? Did you go back and, look at that?
Yeah, so the original specification that we had was just like a time that we had anticipated, or like a time that we had it was more like a goal that we had wanted. But in terms of the actual, the biggest contributor to the 10 seconds, that would be the data transmission time. So the initial 5 seconds, the 5-second interval timer, that was kind of hard coded in. So that was set for both the specification and the observation time. However, the data transmission time was the real key factor that we found to be a lot longer than we had originally anticipated it to be.
Any other questions?
I just want to say your presentation was amazing. It was very good. It was very well thought out. One question that I had, I know it would cost a lot more, but why is there 2, 3, and 4 car trains? Wouldn't it just be simpler to just have it all as 4? Is there a reason?
So the one line was typically only 4 and 3 cars. With the addition of the 2 line, supposedly Sound Transit runs more 2-car trains just for, I think, less ridership. So they try to vary it based off of how much anticipated passengers they have. Right, so then they would run only 4. They would run always 4, but sometimes the 2 line will have 2-car trains. And since they connected the 2 lines, now we have 2-car trains running on the 1 line too, or the 1 line track, I guess, the 2 line, but on the same stations. And so that's how they had this problem.
I was wondering if you guys were using like a range of key values, or do you have one static key for every train car?
Yeah, that's a great question. So how it works is for our key tags, we have just one static tag that was used across all of the tags that we had tested, but it'd be very easy to implement a variety of keys across different tags. And we leave that option for Sound Transit to encode whatever message they want to be as the key.
Thank you. We'll have a 13 minutes break. We'll come back at 2 p.m. for the next session.
Grid harmonization techniques aren't usually applied to museums, since the galleries have strict environmental requirements to protect the condition of the art.
McKinstry tasked us with coming up with some ideas for grid harmonizing the building without compromising the integrity of the artwork. We came up with 3 ideas.
The strategies are battery energy storage system, phase change materials, and non-gallery load shedding.
If you're interested in hearing more about these unique and innovative strategies,
feel free to stop by our poster or our presentation and learn how we keep the grid and the gallery in harmony.
Oh man, what's the data center? I've been hearing all this talk about data centers. I just wish there was a way for me to learn what it was.
What if we have a Lego version? Like we can just plug and play a mini version, a smaller data center.
Introducing Winter River. A modular data center training simulator. Built in partnership with Amazon Web Services and Seattle University. Every search, every stream, every message sent, all of it lives somewhere. Winter River. Learning starts here.
Hello, we are ECE 26.2 and our team is sponsored by Sound Transit. They are the regional public transportation agency in the Puget Sound area, serving millions of passengers across their various services. Our project focuses on their Link Light Rail. When a 3 or 4 car train pulls into a station, it will stop at the designated 4-car sign at the end of the platform. This ensures that tactile wayfinding paths on the platform floor perfectly line up with the 2nd and 3rd car doors, allowing passengers who are visually impaired to easily find their way onto the light rail. However, when a 2-car train enters and stops at the end of a station, one of these paths lead to a spot with no car, resulting in a safety hazard. Sound Transit has tasked our team with designing a lighted platform berthing marker that will illuminate when a 2-car train pulls into a station. This system must be able to reliably count the number of incoming cars and light up a sign if a 2-car train enters, indicating to operators where they should stop. This solution aims to uphold Sound Transit's mission of improving public transit for all passengers, ensuring high quality, safe, and inclusive transportation for everyone in the Puget Sound. We look forward to seeing you at Projects Day 2026.
Hi, we are Team Interdisciplinary 26.1, a mix of mechanical, electrical, and computer engineering students, working alongside McKinstry to help optimize SUMA, aka the Seattle University Museum of Art.
museum use a lot more energy than other buildings, so our task is to compile a list of optimization strategies to keep the artwork safe in the art storage and exhibition areas, and to keep the general public area very comfortable.
Following industry standards for heating and cooling in museums, we researched and calculated the ideal HVAC and lighting set points to achieve the most energy savings.
We used industry standard simulations of the building baseline for HVAC and lighting and created an hourly schedule with temperature set points modeled after the control strategies we chose and compared until we achieved maximum energy savings.
Anyways, with the simulation results, we used Excel to perform analysis and calculations to determine what factors give us the best energy savings. Join us on Project Stay to learn more.
LiDAR and tracking camera systems are powerful but often rely on expensive proprietary hardware. Working with Metrola, our Seattle University design team built a cost-effective modular alternative. We started by designing a universal aluminum mounting bracket to hold commercial off-the-shelf sensors. This setup gives us industrial performance for a fraction of the traditional cost. To make the sensors work together, our software pipeline takes the real-time LiDAR point cloud and fixes it to detect specific targets like pedestrians. The system then instantly translates those 3D coordinates into precise pan, tilt, and zoom commands, keeping the subject perfectly in frame. Everything runs locally on an edge computer and a router, delivering a highly scalable and adaptable tracking solution.
Welcome to the metal-rich asteroid Psyche 16. It is located between Mars and Jupiter, approximately 300 million miles from Earth. Exploration of this asteroid has just begun, with an orbital projected to reach in 2029. Until then, scientists are not fully certain of what terrains are on the asteroid's surface. Back on Earth, a team of engineers is working hard, designing a rover suited for the potential terrain it might encounter. Sponsored by the NASA Psyche mission, the senior design team INT 26.4 is proud to present our rover design. Our approach embraces the traditional rocker bogie suspension system, controlled by a LiDAR and Raspberry Pi operating system, powered by an 11-volt LiPo battery, all compiled in an acrylic housing.
Hey, is that Origami Robotics?
No, it's not. But you know what is?
Seattle University INT 26.5.
NASA Psyche mission, Origami Robotic Exploration Team.
Testing. Hello? Members, hear you guys.
Come to Project Day to learn about our research into origami robotics application for space exploration on asteroid Psyche. See you there.
What is up, everybody? We are
team INT 26.2. We're a team of mechanical and electrical engineers working with McKinstry on grid harmonizing the Seattle University Museum of Art.
But what is grid harmonization?
Glad you asked. Grid harmonization is the process of shedding or shifting building electricity demand to reduce stress on the electrical grid.
Grid harmonization techniques aren't usually applied in museums, since the galleries have strict environmental requirements to protect the condition of the art.
McKinstry tasked us with coming up with some ideas for grid harmonizing the building without compromising the integrity of the artwork. We came up with 3 ideas.
The strategies are battery energy storage system, phase change materials, and non-gallery load shedding.
If you're interested in hearing more about these unique and innovative strategies, feel free to stop by our poster or our presentation and learn how we keep the grid and the gallery in harmony.
Oh man, what's the data center?
I've been hearing all this talk about data centers. I just wish there was a way for me to learn what it was.
What if we have a Lego version? Like we can just plug and play a mini version, a smaller data center.
Introducing Winter River, a modular data center training simulator. Built in partnership with Amazon Web Services and Seattle University. Every search, every stream, every message sent, all of it lives somewhere. Winter River. Learning starts here.
Hello, we are ECE 26.2 and our team is sponsored by Sound Transit. They are the regional public transportation agency in the Puget Sound area, serving millions of passengers across their various services. Our project focuses on their Link Light Rail. When a 3 or 4 car train pulls into a station, it will stop at the designated 4-car sign at the end of the platform. This ensures that tactile wayfinding paths on the platform floor perfectly line up with the 2nd and 3rd car doors, allowing passengers who are visually impaired to easily find their way onto the light rail. However, when a 2-car train enters and stops at the end of a station, one of these paths lead to a spot with no car, resulting in a safety hazard. Sound Transit has tasked our team with designing a lighted platform berthing marker that will illuminate when a 2-car train pulls into a station. This system must be able to reliably count the number of incoming cars and light up a sign if a 2-car train enters, indicating to operators where they should stop. This solution aims to uphold Sound Transit's mission of improving public transit for all passengers, ensuring high quality, safe, and inclusive transportation for everyone in the Puget Sound. We look forward to seeing you at Projects Day 2026.
Hi, we are Team Interdisciplinary 26.1, a mix of mechanical, electrical, and computer engineering students, working alongside McKinstry to help optimize SUMA, aka the Seattle.
Yo. Hello? Oh, it's on.
We wait for a prompt, I think.
Testing.
Okay, welcome everybody to Project Day, the culminating experience of all engineers and computer scientists and some of master students at Seattle University. My name is Theodora Schumann. I'm a coordinator for mechanical engineering, but today you're going to hear some mechanical and electrical and computer engineering projects in this session. So I'm going to open the floor here to Dr. Eric Gilbertson, who you may have heard about. He's the one who discovered that Mount Rainier is a little shorter than we originally thought. So Dr. Gilbertson, can you please come on, and he'll be introducing the teams and emceeing this session.
Thanks, I'll be moderating the session. So the first talk is 30 minutes. It's a joint ME and ECE talk for a project sponsored by Amazon. So 30 minutes of talk and 10 minutes of questions.
All right, I guess let's get started. Good afternoon. We are Team ECE and ME 26.1, Team Winter River. We're working in collaboration with Amazon Web Services, or AWS, and Seattle University to bring you guys an educational, hands-on data center design. But beforehand, let's introduce our two sides of our teams. Like we said before, we're two separate teams, but we work together. On the ECE side, hello, my name is Leilani Gonzalez, computer engineering major.
Hi everyone, my name is Adam, electrical engineering major.
My name is William McDonald, electrical engineering major.
Hi, I'm Ezekiel Mitchell, computer engineering major. I'm Keshav Verma, I'm an electrical engineering major.
And for the mechanical engineering side, hello, I'm Anthony Rios.
I'm Austin Lowe.
I'm Israel Boyd.
And I'm Rowan Halpern.
Our sponsor is Eric Crompton, a product engineering specialist at Amazon Web Services who specializes in data center design.
And for the faculty advisors on the mechanical engineering side, we have Dr. Mosen Dadvarnia.
And for us on the ECE side, we have Dr. Swetha, who's an ECE department professor here at Seattle University. Here's a quick outline of what we're going to be going over today. We're going to give you guys an introduction to Amazon Web Services, our product specifications, the details, the budget, finally, and then a demo video, perhaps.
So Amazon Web Services is a cloud computing platform offered by Amazon. They offer businesses and individuals a wide variety of services, including computing, storage, networking, and many more that we all use on a daily basis. In fact, pretty much everybody in this room indirectly interacts with the data center every day without even realizing it potentially. Whether you're sending an email, asking something to ChatGPT, or storing something to iCloud, there's a data center in the works somewhere in a rural area. And whenever we say something is stored in the cloud, that simply means a data center. So think massive rows of power distribution equipment, cooling infrastructure, all sorts of different server racks and intricate equipment that powers our digital lives every day. And AWS has experienced explosive growth over the last few years. With the rise of AI, there's been an increase in demand for faster computing, and they currently operate over 100 availability zones worldwide. However, this has also unveiled a critical challenge, where training programs can't keep up with the demand for new data center technicians.
All right, so let's go over the general layout of a data center. So the infrastructure is built around the computing of servers. These servers are stored on racks and aligned in rows, held in large rooms called server halls. The power is brought in from utility grids externally and then conditioned and brought into the facilities where it is distributed to the server halls and the cooling infrastructure which keeps those servers from overheating so that they can operate efficiently. So let's go further into the cooling. So cooling takes a big part of the power load, which is why it is important that it runs efficiently. So one of the main types of cooling used today in data centers is air cooling. And the way that this works is that cold air is sent into the front of server racks, creating a cold aisle, as you can see in blue. Then when these servers are used, they expel heat out the back, creating a hot aisle, as you can see in red. Then this air is then exhausted to the outside, or it is recycled and reused in the cooling process. The reason that this system is used is to prevent hot air from mixing with cold air so that you can efficiently cool the air without needing more power. So one of the types of air cooling used today is evaporative cooling. The way that this works is that air is brought in from the outside using fans, and then it passes through an evaporative pad. And this pad is just a pad which is being fed water with a motor. And then when the water evaporates, it takes heat from the air, cooling the air before it goes into the server halls.
So the primary Server racks and cooling are the primary electrical loads in the system at a data center. To power this, we need a significant but common power distribution system. So here you can see the utility, transformer, distribution, and then backup generator and UPS. This is a pretty simple and common industrial power distribution system. And this is something that we wanted to capture in our model. So some important things about this diagram here are utility power. We have both an A and B side. This is called redundancy. And then we also have our backup sources, which is a diesel generator. And just like your car, it has a startup time. In the meantime, power would be fed by the UPS or uninterruptible power supply. And you can also see there are some dashed lines here and here, which is indicating transferring, which is when you switch over from one power source to another.
So let's go over the motivation for our project. Our objective is to train new technicians on how a data center operates. The problem with this, how this is done now, is that making a mistake in a live data center environment can shut down critical infrastructure. This creates a need for a low-risk training environment to teach technicians about data centers. So our solution is to develop a physical representation of a real-world data center, simulating its cooling and power operations.
So to achieve this goal of building a tabletop data center, there were 6 key specifications that we had to establish. First of all, we needed a wireless communication scheme, and that's where MQTT, or Message Queuing Telemetry Transport, comes in. We also needed a way to power each data center component that's being simulated, which is where the printed circuit boards come in, that were customly designed and deliver power to each node. We also wanted this to be modular, so we wanted the user to be able to treat this like Legos. Take a data center component, move it somewhere else, unplug it, and see what happens. We also needed a way to simulate or display our simulated power values, which is where the OLED node displays and the centralized Grafana dashboard comes in, which essentially acts as a display and tells the user the overall system behavior.
So here's a physical walkthrough of our design solution. So we are using a Raspberry Pi, which is a small computer, to run our system models, which will then be outputted on a user interface where the user can interact with the model outputs. The Raspberry Pi will be housed in a base plate, which will also house our circuit boards and our power bank to power our system. We'll be using modules as visual enclosures to represent real-life data center components. It will house a microcontroller to communicate with the Raspberry Pi, as well as hold a small screen to display more relevant information. So here's an example of how our system will work. A user will place down a module, and our system will detect it, and then give certain outputs depending on what module was placed. So for example, some variables that might be shown are total power, efficiency, or cooling load.
All right, so this is the overview architecture of our Winter River system. We divided our system into 4 main layers to keep the design scalable and modular. First one would be the physical, second one communication layer, third one simulation layer, and final the visualization layer.
To go into more detail about what Adam was talking about, I'm going to explain kind of the flow of our whole 4-layer system. So first, we have that physical layer. So those are everything that you see placed right here in front of me. So that's going to be the nodes, the ESP32s, the actual base plate. It's then going to lead into our communication layer, so how everything's talking and transmitting data amongst each other, or the Raspberry Pi to the nodes. That then feeds into our simulation layer, so all of that actual power flow logic, the thermal equations, and handling that whole communication layer. Finally, into the visualization or data layer, which is you're going to find our PostgreSQL database, the nodes table, and the thermal zone tables. And this leads all the way back to that physical layer through those OLED displays. First, physical layer.
So we're gonna step deeply into the physical layer. The node is the fundamental building block of our overall system. Each node represents a piece of data center in the real life, which suggests transformer, utilities, switchgear, or cooling unit. And on the top of the enclosure, you can see the OLED display. We use 0.96-inch display to show all the live status. These displays show all the information such as system behavior, voltage, current, and inside the enclosure, there would be the ESP32 microcontroller acting as a processing and communication unit. And we also use the I2C. I2C stands for Inter-Integrated Circuit, which is a simple communication protocol that allows multiple electrical devices to communicate via Wi-Fi using the MQTT protocol. We choose ESP32 The best reason because it has a low voltage connected to Raspberry Pi and then support positively to the entire system.
To build a realistic environment, we narrowed the facility down to 7 primary components covering computing loads and cooling infrastructure. Our goal was to create a module that visualizes and simulates features and functions of its relative components. First, we have the utility power. In real life, it pulls high voltage electricity from utility grid into the data center. And here's our module that we designed, which is roughly 3 by 4 inches. In our training model, it provides simulated power to all connected module components. And for the transformer, in our training model, it displays simulated voltage entering and leaving the unit that goes into the switchgear. In our simulation, it routes power to connected components. And this is the core. This is the server rack, which processes, stores, and transfer data. Each server module represents 100 racks. And we have 3 data types that are server, storage, and AI, taking up 20, 32, and 100 kilowatts per rack. In our simulation, the server module would draw power and spike cooling demand, and that's when the operator would plug in a cooling module to lower the temperature and increase airflow. And each cooling module represents 55 evaporative cooling. And during a power outage, the UPS, which is the battery, would provide instant power backup until the backup generator kicks in. Finally, we have the backup generator that provides extended power during a utility outage.
So next is the base plate. This is where all the physical component nodes that Austin just talked about live. And we actually have our model right over here, so you can see what I'm talking about. But we have a figure here that gives you a little bird's eye view of what the base plate is. So it serves as the foundation for powering and mounting each node. You'll see we have 4 printed circuit boards that are distributed across the base plate. And this system housing is the black, that refers to the black acrylic laser cut rectangle you see there, which essentially gives a mounting platform for the PCBs, the Raspberry Pi, and other power electronics equipment. And this supports node modularity because we have USB-C plugs that a user can simply plug and unplug components into. And this is actually a little bit of an up-close render of one of the PCBs. All of the PCBs look the same, and they're simply used for power distribution, nothing else. You'll notice that there's 6 squares, and each one of these squares is called a courtyard, meaning there's no electronic components of the PCB that are placed into that part. So it's physically reserved for the components of the data center, so there's no interference whatsoever. You also see that in the center of each square is a USB-C plug, and that's where each of our nodes plugs into. Along this, you'll see a large power trace that distributes power to each node, and you'll see a USB-C receptacle at the far left, which distributes power, which I'll define right over here as a high-level overview of our power architecture. At the core of this all is the Anchor Prime desktop charger, which is essentially a USB hub that's capable of delivering high power. So each PCB is powered through a USB-C receptacle, and you can even see through the animation, or through the squares here, we have different spots reserved for the nodes to convey that point. You also see that the Raspberry Pi is powered by the Anchor Prime charger, as well as the 14-inch touchscreen display. And those two are connected through USB-C, and that essentially enables the touchscreen capability of the touchscreen. And this is all powered through a central wall outlet, just standard 120-volt AC. And this Anchor Prime desktop charger is actually capable of 200 watts, which seems like a lot, because it is, but we have a peak power consumption of 94 watts, and that's pretty unlikely to reach in the first place. So we have plenty of headroom to work with.
Okay, so let's talk about some mechanical supports. When you're placing a module, the PCB tends to flex downward due to the force. So we decided to design some supports for our PCB. Here's what our support looks like inside of our base plate. We also decided to create a support that goes on top of the PCB so that when you're taking a module out, it doesn't flex the other direction. Here's an exploded view of our
base plate so you can see how it's assembled. First, we have our acrylic walls and lid. The acrylic lid has 24 cutouts to fit, in order to fit all of our modules. And the acrylic lid rests on 8 acrylic blocks that are glued to the walls and corners of our inner walls. Inside of each of those blocks, there are heat sets. And these screws screw into those heat sets, securing our lid down. In the inside of our base plate, we have our 4 PCBs, which power our modules, that are stood up on standoffs and supported by our supports. Underneath our PCBs is a Raspberry Pi, which wires directly into our Anchor power supply, and they are both conveniently placed under one board for easy maintenance. The wires wire out through the cable pass-through that's cut out through the wall. Here's a full base plate CAD assembly view.
Now for the second part of our architecture, which is the communication layer. So first, let me define a communication protocol to you guys. It's basically the rules that govern how data is transmitted between 2 devices. So in our case, you keep hearing us say MQTT, MQTT. That's basically one type of communication protocol that works as a publish-subscribe. So we have all these nodes can be either a publisher or a subscriber, but they all talk to one central brain, which is our Raspberry Pi, which is a tiny microcomputer. So let's say, let me run you through an example. But first, let me explain why we chose MQTT. It has this feature called last will and testament, which allows a message to be pre-programmed to be sent out to that center brain in case something happens. Or something happening is it's disconnected from power, it's dead. So we have this central computer, this Raspberry Pi, and we have our nodes. Let's say a physical event happens and they're unplugged. It's then that pre-programmed message is removed. It tells the brain, hey, I've been removed. So it reruns, it receives that message, it reruns those calculations, so whether that be the thermal calculations or the voltages, whatever it may be, and the physical results is all the OLED displays are then updated. So let's say it was something that causes all the servers to go down, this is what our server rack would look like. It would say it's offline, there's no pressure, the cooling's gone, there's no voltage in or out. Next is the simulation layer.
For our simulation layer, we actually use Python on the Raspberry Pi as our main brain logic. And what that does is handle all of our simulation. So our cooling, our temperature, our fans, that's going to take care of all that big brain work. We use our ESP32s, which has their each individual firmware on it, which pretty much gives it identification. Is it a server? Is it a transformer? Is it a utility? It's going to give it its ID, which transfers that information, as Lonnie said, via MQTT to the actual Raspberry Pi. That Raspberry Pi is going to take that data, aggregate it with SQL, and then send that information to the actual Grafana dashboard, which shows up on that screen there. And that's going to allow the actual trainees to look at the screen without having to identify each and every single minimal problem for every individual node. So the screen acts as pretty much an overall display of how the system's working as a whole.
Okay, so let's talk about the computer models. So we have 2 models that calculate the cooling for our simulated data center. These models are written in Python, and they live in our Raspberry Pi in the base plate. So what you're seeing here is just a cartoon of the actual computer models. So we start with warm air outside of our data center. That air passes through the evaporative pad, cooling down. It will then pass through these fans, through the ducts, and into our cold aisle. So this cold aisle is the air before our racks. The air will then pass through the racks into our hot aisle, taking the heat with it. This hot air is then sent through more ducts, and then either to the outside or recirculated back through our data center. So what goes in and comes out of these models? For our inputs, we have the number of servers. So you can think of this as the number of data modules the user places down. We then have the number of fans. This is like the number of cooling modules the user places down. And then finally, we have the weather preset, which I'll talk about on the next slide. This is all fed to 2 models. We have the pressure model, which calculates the pressure difference across a rack. And then we have the temperature model, which calculates the hot aisle temperature. These models are independent from one another, meaning the output of one has no effect on the outputs of the other. For our outputs, we have the PUE, or power usage effectiveness, You can think of this as an efficiency of our data center. We then have T hot, which is that hot aisle temperature. We have the power consumption of the entire facility, and then we have that pressure differential across a rack. So for these weather presets, the weather presets allow the user to select a weather condition from an available list. These conditions are relevant to current AWS facility locations, and they're combinations of hot, cold, humid, and dry, which shows the range of cooling for evaporative cooling and how it performs under these different conditions. So our first model, the pressure model, we start with our intake fans. This will raise the pressure of the air. It will then pass through the ducts, which will lose pressure due to friction until it gets to our racks. We have this pressure drop through the racks, which we denote delta P rack. And then finally, we have more pressure losses through ducts due to friction. The purpose of this model is to calculate that delta P rack. And what it checks for is if that pressure difference is above or below 20 Pascal. If the difference is below 20 Pascal, the model will report that the system is overheating. And the reasoning behind this is if we have an insufficient pressure gradient, the hot air leaving the racks can actually flow back into the racks, causing the overheating. The assumptions we make, so the big one we assume is that the fans operate independently. So what this means is in reality, fans are very complicated and they have these performance curves, where if you change the number of fans, the shape of the curve will change. We're putting that aside and we're saying things are gonna operate in a linear fashion. So if you add a fan, the pressure will increase linearly. We are also assuming steady state, which means that there's no transient effects. So if I place down a model, everything instantaneously updates. The reasoning behind this is it's just easier to calculate and it puts less strain on our Raspberry Pi. Finally, we're going to neglect other forms of pressure loss. We really care the most about this delta P rack, so things like pressure leaving out of the ducts through little gaps, that's not of importance to us, so we're going to neglect it. Our second model, this temperature model, we start with the dry bulb temperature and the relative humidity outside. These come from the weather preset. That air is then sent through the pad, through the fans, into our cold aisle, through the racks, and into our hot aisle where we get this TH, which is the hot aisle temperature. And the purpose of this model is to check if that temperature is above or below 120 degrees Fahrenheit. And if it's above 120 degrees Fahrenheit, the model will report that the system is overheating. And the reasoning behind this is just a standard for how the maximum temperature of that hot aisle should be. The assumptions we make are that this evaporative pad is bringing our air up to 85% relative humidity. We are again assuming steady state for the same reasons outlined previously, and we are going to say that servers are the only heat source. So because we're trying to calculate this hot aisle temperature, we don't care about heating from lights or say like the toaster turning on in the break room. We're going to throw all that out and just focus on the servers. And then finally, we're going to assume constant air density. So in reality, the temperature of air the density of air will change as the temperature changes, but it's a very small change, so we're putting that aside as well.
Our final architecture layer is our visualization layer. This is what the user is going to interface with. So we have 3 tools for doing that. The first is the OLED on the top of the node. This shows equipment-specific data. For example, it'll tell you about the transformer, what voltage is coming in and what's going out, the primary and secondary. We also have 2 on our touchscreen interface. The first is a Grafana dashboard. This will show historical data. For example, if there's a power outage event, it'll show you how that changes, how the system changes over time during that event. And finally, the touchscreen user interface. This allows the user to input some values, such as changing the number of fans or other things that you can't do by just placing modules in and out.
All right, so the total budget of both teams would be around like 2,000. So the ECE team, we spend about 1,200,000 for mostly for the PCB fabrication, is B32 OLED display and all the electrical components. And for the ME team, spend around $600, mostly for the PLA filament frame material, base plate, other print, and materials. So far, this purchase allow us to do both electrical and mechanical portion of the Winter River system.
And finally, mechanical team has 4 future recommendations for improvement. First, our current current power and cooling model assumes a steady state condition. Upgrading to a transient modeling will allow the operators to see the variable change over time, leaving them a realistic window to react to an emergency. Second, we recommend adding other cooling method. It could be liquid cooling along with system redundancies to match modern infrastructure. And third, in a real data center, airflow is never perfectly constant. Therefore, incorporating accurate fan dynamics will make the pressure model much more realistic. And lastly, future iterations should focus on mass manufacturability.
On the ECE side, our recommendations are there to help the user better visualize what's going on. First of all, we'd recommend that future iterations incorporate some sort of LED traces built into the base plate that can clearly convey the primary and secondary power and cooling flows. Second, we'd recommend that future iterations have power indicator LEDs on each enclosure. So if there's normal operation, if it's receiving power okay, have it green. If it's starting up, yellow, and if power's out, we can change it to red. We'd also like to extend a thank you to Eric Crompton, our liaison engineer from AWS, as well as Trey Board. And here at Seattle U, we'd like to extend that thank you to the Project Center, Dr. Dadfarnia, Dr. Varadarajan, and Dr. Miguel. None of this would be possible without you all. We'd like to open the floor to questions now. Thank you.
What are some of the major concerns when designing the PCB for this?
The biggest concern was making sure we can have enough current flowing through the traces, because we assumed a worst case scenario that each ESP32 would draw 500 milliamps, which is a fair assumption. And the trace was sized such that it can supply 3 amps. So 500 milliamps times 6 ESP32 nodes, 3 amps right there. So we used a calculator that was compliant with the IPC 221 standards that gave us the proper size to make the trace with, which gave us a size initially of 53 mil, but we decided to upsize that to 80 mil because we wanted to have that extra margin, just in case there was some sort of fault current or for whatever reason, if we needed that extra tolerance. I was curious why you guys decided to do 5% relative humidity. I feel like that's a little bit high compared to
Yeah, so we talked about this for a while. There is a range of relative humidity that you can choose. That number is actually given to me by an AWS employee, so I felt safe using it. But you're right, there's a wide range. But if it comes from AWS, it felt pretty safe.
Any other questions? What's the plan going forward? What's Amazon going to do with your final product?
We're building next year. AWS is targeting the next 2 years, tens of gigawatts of data centers. So Amazon's going to build tens of gigawatts of data centers, and that's just Amazon. And then there's Microsoft and Meta and everybody else. And I think our forecast is that we need 10,000 electricians. We need thousands of data center technicians that we have to, and then our customer, everybody in the world that needs to understand, all of the media, all of the complexity of the utilities, the water, the resources that we're using. How do we communicate to everybody how the data centers work, what services we're providing, these kind of resources to be able to inform people, whether they're working in our data centers or customers using our services. How do we communicate with our customers or our, the people we interface with? And how do we train the future, all the STEM programs that we should be supporting? It's easy. We want to use all of our digital services, but there's only so far that you can go. Having something tangible that you can put in front of a student, in front of a future employee, and say, look, here, this is what you're looking at, a data center. It's, it covers acres and acres, but this is what these fundamental components are. So the plan is to iterate on this and make this more precise and make this more functional and add in additional devices and evolve it to include our next data center designs. So that's where this goes next.
So along the same lines, I want to ask the students if they can answer this question. So let's say you're training these 1,000 different potential people who will be working in here in these data centers, and you can bring this model to their place of where you're training them, which is close to their homes. They don't have to travel to a single spot. Is that going to provide some savings, that will bring this development a little bit more sustainable than it is right now by doing that? So if you can answer that, I would like to hear.
I like this question because I got to test it out on a different thing. One of the beautiful things about this system that my team and I have come to realize is not only when it comes to savings, but when it comes to politics. So let's say, for example, I'll touch on the savings one next because I feel like this one's more important. When it comes to certain political events, right? Let's say we can't go here, we can't go there, this country can't come here or there. One thing the systems can do is, number one, it's secure. It's not utilizing Ethernet, it's not utilizing Wi-Fi, it's only utilizing the access point hosted from the actual Raspberry Pi. So theoretically, you should be able to plug this in to a generator, take it to the bottom of the ocean, and it operates as normal. So with that being said, you can pack this system up, which Eric is going to do, pack this up and steal it. You can pack this up, take it to somewhere like Shenzhen, China, Blackburn, UK, which a company that I work for have offices in both. And sometimes we need to say, hey, what do you have in your lab? Hey, what do you have in ours? Oh, we can't get there. Can you just ship it? So imagine being able to pack this up, ship it to Shenzhen, China, let them test it out, see if they want to even work within our own data center. So let me backtrack. Imagine you own a data center, and then you build a model like this, a replica of your actual data center, where it simulates live time, and then you can have trainers run on it. You ship that over to a country, and then say, hey, this is what we have. This is a replica of what we have. You don't need to come over, do a walkthrough in person. You don't need to do any of that. Is this something you're interested in? These are the values it can take. This is what we can support. Is that something you're interested in? There's also other ideas that we talked about during our tour at the data center, which I'm probably not going to talk about here, but there's some pretty cool ideas that you can take this and expand onto it. Now with the savings, that's also a good one. Think about training, how much it costs to fly someone in, train them on these systems, just to find out, oh, you're not even good at the job. So imagine building these at large scale, shipping them out all over the country, and then having pretty much workshops with these to see if people are not only interested in working in a data center, but able to grasp the information quickly, and just seeing who has that natural data center ability. So it saves time, it saves money, and it saves travel, which falls into both of those categories. Does that answer your question?
It's easier on them, it's easier on their families, so they don't have to travel as much.
Right.
And it's better for the environment. We agree with you.
Exactly. Much better for the environment because that's less plane rides, that's less trains, that's less cars. It's just, where do you want to ship it?
Okay, let's thank the Amazon team.
We'll do live demos upstairs. Don't worry.
Yeah, let's set this up. Can I just take this one out? You have to do this one because this one has all of the this is plugged in. So we'll plug both of them. Yeah.
these two after I said. Okay, we're ready to start the second presentation. This will be a project sponsored by HeatCon with a mechanical engineering team.
All right, hello everyone. We are Mechanical Engineering Team 26.2, and we have made the wire winding machine. My name is EJ Idora.
I'm Ava Weiss.
I'm Taryn Foley.
I'm Larissa Taramora.
And I'm Hikaru Hayano.
We want to give a special shout out to our faculty advisor, Dr. Joshua Hamill. He's hiding back there, but he's over there. Our sponsor company, HeatCon Composite Systems, and our sponsor liaison, Patrick Bautista.
So starting off, we got a little bit of background on the problem. Over at HeatCon Composite Systems, they manufacture aircraft parts, and these aircraft parts are made of composite materials. Now, these composite materials need a very even heating on them for them to set correctly. Now, this heating is achieved with a heat blanket shown here, and that heat blanket is woven from a heater cable. Now, that heater cable, it's very important that the resistance along it is controlled as possible so that the heat output by that cable is as consistent as possible along the length of that cable. Now, that heat cable is composed of a core thread made of Teflon, and that is wrapped with 2 metal outer wires. Now, zooming in on that wire winding process here, we first start off by feeding in that core thread with a known tension and wind rate, or feed rate, and then wrapping that with 2 metal outer wires at known tensions and wind rates. And then that outputs our resistance-controlled heater cable.
So this is the current machine that the company uses to make these wires. Some overview on how this works. We start here at the core thread, which is fed into what we are calling the splicer. This is where those 2 metal wires are being wrapped around this core thread and then output here onto the resistance meter. This measures the resistance, and then we finish by spooling it out onto our end spool. So for our design, we wanted to update some key parts of this system. What we have is we want to measure and control our tension of both the core spool and also the wire spools better. The way they do it now is just by hand, and the operator just tightens the spools onto the machine based on how it feels. So we want to make sure this is more reliable and repeatable for them in the future. We also want to make a more reliable safety cage. If anything goes wrong, any spools fly out, we want to make sure that this is uncrackable and safe for them to use. And then lastly, we want to modernize the user experience. This machine is about 30 years old, so we have a ton of wires and buttons going on this big box. We want to just make sure that this is simplified on one laptop where we can give inputs and get outputs all on one program.
So the design requirements we're given are to produce a whole new wire winding system, control the tension on that core thread as well as how fast it's being fed through the entire machine, control the tension on those outer wires and how fast it spins around that core thread, measure and record product wire resistance in real time, and improve user experience as well as the safety of the entire operation. So to do that, we split this project into 5 major components. So we're going to start over there on the right side with that core thread, and that will be fed through into our splicer right here, and that will be enclosed by our safety cage, finally going into the resistance measurement to go through the winding guide onto that output spool.
So starting with our core thread, this right here is what they have on the current machine that they're using. This basically is our hand-tightened screw that screws in and pushes this piece of plastic against the spool base like a friction brake. So to make this more measured, we're replacing this with a linear actuator here. This uses a motor and a worm gear to push this orange piece out, and therefore we can give an input distance for this to go. So for our core spool assembly, we have here in yellow is what would be our core spool. This is sitting on top of our spool base, which has our shaft is freely rotating, which is where our linear actuator comes into place. We have this set up to press against the spool base, and in between the linear actuator and the base, we have a spring and a felt pad to allow for more variable pressure to put against this.
So moving on to the wire splicer itself, we start off by feeding in that core thread from the other side of that drive shaft all the way through the drive shaft and into the main body of the splicer. The splicer then rotates around that core thread, causing these two metal wire spools to unwind onto it, which then outputs our final heater cable. Now, similar to the core thread mechanism, there is another linear actuator shown here that extends into this block, which houses a spring with a felt pad at the other end, and that can adjust the amount of tension on the metal spool wires as they wrap around. I also want to point out that we have a bolt going all the way through the spools here, so that at any point there's no chance that these spools can fly off the machine.
So moving on to the safety cage structure, which encloses the splicer that Taryn just described. The first component of this safety cage is a aluminum skeleton structure made out of L-shaped aluminum extrusion for extra stability and structure. Attached to the back of this aluminum skeleton are two hinges placed here for easily accessible opening and closing of the cage so that you can quickly remove or attach those rotating spools that Taryn was talking about. On the exterior of this aluminum structure, we added 1/2-inch thick clear polycarbonate so that the user can easily view the inside and see the splicer rotating, as well as adding a stronger crack resistance compared to the plexiglass, which is currently used by Hecon right now. We also added an emergency stop right here for additional safety as to when the cage is open, the splicer stops running, and only when the cage is fully closed can the splicer run.
All right, so for a resistance measurement system, it's essentially a quality check, right? So let's take a look at what they have right now. So their current design, we got wire coming in from the right side. It's wrapping around these cylinders, measuring out 10 feet, and it's being output on the left. We got 2 contact points here where we're sending in a current, and with that, we can measure a voltage drop, and that's actually how we find the resistance. So what did? We decided to go with the vertical orientation. Starting from the top, we got an electrical slip ring. This just allows one set of wires to stay stationary as the others can spin freely. That connects to our custom spacer that then allows us to connect to our Delrin cylinder, which is a plastic cylinder, helps us measure out that 10 feet. That connects to our brass cylinder, which is our contact point where we're sending in the current and measuring the resistance. And that's sitting all on top of a thrust bearing. All right, so here's a little wire diagram to make things a little easier to understand. So first we got 3.3 volts going into our system, and we got our wire winding all around, measuring 10 feet. To complete the circuit, we gotta ground it. But hold on, we're not actually measuring the resistance. What do we gotta do? So first, we gotta add a resistor where we know the value of. Then we gotta add a voltage out measurement right after the resistor. And using our classic voltage equals current times resistance, we can find the current running through our whole system. Then we can find the resistance of the wire using this simple equation, V out over the current.
Okay, finally, towards the end of our machine now, we want to make sure that our end wire is spooled onto the end spool evenly so it doesn't get bunched up on one side. We use a winding guide very similar to another machine that the company already has. And so taking heavy inspiration from that, we use a quick return mechanism to turn our motor's rotary motion into the linear back and forth that you see here on top.
So to improve user experience, we designed everything to be controlled by one computer. So to do that, everything will be connected to an Arduino, which is a microcontroller, basically just telling everything what we want it to do. So with the linear actuators, if we want to increase the tension, we send a current in through that red wire and then ground the black wire, and they'll start to push out. If we want to do the opposite and have them retract, we send a current through that black wire and then ground the red wire. Each motor will be connected to the Arduino with their own personal motor drivers, and those are basically just handling the power all from one singular power source and communicating between the Arduino and the motors, telling it how fast to spin and which direction to turn.
So moving on to our team's attainment of the requirements given to us by Hecon. So first of all, we were successfully able to produce an entirely new wire winding system as shown here. We were also able to control the core thread tension and feed rate utilizing the linear actuator as Ava described. On a similar note, we were also able to control the outer wire tensions as well as the rotations per minute, utilizing 2 linear actuators attached to the interior of the splicer. Additionally, we were able to measure and record product wire resistance in real time with the setup that Hikaru described, as well as the readings as shown via Arduino. We were also overall able to improve user experience for operation, as all of the electronic components are controlled via Arduino and therefore one computer. So any adjustments that need to be made can just be adjusted on the code as shown on the left and with the setup on the right. Finally, we were able to improve the overall safety of operation with the bolt going through the entirety of those outer spools so that the spools are much more secure while rotating. Additionally, we tested the impact resistance of the polycarbonate as shown here, and it is much stronger than the plexiglass, as well as the implementation of an emergency stop.
So our main priority was to produce a machine that could satisfy all the design requirements within our time and our budget. But before we pass this on to Hikon, we've identified 3 potential improvements. So with the linear actuators, they are able to control the tension, but they don't have encoders. So what that means is we have to calculate both position and tension by hand. So we recommend purchasing linear actuators with encoders because it would make the changes much more precise. With the splicer, the assembly is much more involved, but that ensures that the spools are super snug in our machine, so we would suggest adding some sort of quick release because it would make the setup much easier and much faster. We also purchased stepper motors because we wanted to make sure we could handle the torque coming from that splicer, as well as being able to control them all with one Arduino, but they're limited to 300 RPM. So we would suggest purchasing servo motors, which are a little bit more expensive, but they can spin much, much faster while also handling that same torque. But on that note, thank you for coming, everybody.
All right, I have 2 design questions, if I could. Taryn, I believe you are the one who was working on the spools that go around the core thread.
Yes.
Is there a reason why those spools are as far away from the core thread as they are? In terms of like, could that distance be narrowed and be closer to the core thread? If you understand that, like,
Yeah.
am I explaining that right?
That was a so obviously you want those to be as close as
Yeah.
possible to limit the force.
Yeah.
That was a compromise option because you had to fit the linear actuator and the spring on there. So that's what ended up driving those spools further out. Ideally, for future work, I would probably recommend some sort of lever or cantilever system to maybe change the orientation of that linear actuator. But other than that, yeah.
Right, and then for Hikaru, I was wondering, is that 10-foot number that you're referencing for the resistance measurement an arbitrary number, or is that 10-foot specific for something?
Yeah, great question. So pretty much the 10 feet is what Hikon is using right now. It's sort of an arbitrary number. It's a big number so that you can divide it so that you can find out the resistance per foot. So in the code, it showed the overall resistance and then per foot how much that resistance was. Thank you.
I was wondering, can you estimate how much cost savings your design does for Hikon?
We can't really estimate cost savings as much as this is sort of a prototype for a new wire winder that they're making, and it's more to solve the problem of controlling the resistance of the wire. So their current system has a number of inconsistencies that they'd like to iron out. I'm not aware of how much that costs them over time, so I don't know how much that would be saving them, but effectively this is a machine that's meant to make that heater wire and then those heat blankets more consistent. So I assume there would be some cost savings from less rejected wire from this machine.
For the setup of that machine, it looks like there's a lot of threading and weaving wires to get it all set up. Does this make it easier or harder to set up an initial run?
This makes it likely harder. We haven't seen their original machines be set up before, but at least with changing the spools out, we know that's a lot more difficult because you have so many more parts on that shaft, that bolt there that's sitting there. So that's why we want to like encourage them to add a quick release mechanism. We attempted that, but it was a little bit outside of our time constraint. So yeah, it would take longer to change those spools out. And threading the whole system is pretty difficult. It is a little challenging to get that started, but once it's going, you can run it for a very long time.
It looks awesome, guys. I love seeing the whole thing put all together. One question I have is, now that I kind of understand the purpose of it, let me clarify that. I just want to fully understand the purpose of it. Are you hoping to actively monitor the resistance and change it on the fly? Or is this just a red light, something's wrong, reset situation?
I think the ultimate goal is to monitor the resistance as it runs, and then change those linear actuators given that feedback. That controls problem, again, is a little bit outside of our scope. We just wanted to focus on the mechanical design to achieve that.
So adjusting that wrapping would change the resistance if that?
Yes, there's a number of things. You can change the wind rate. Those are usually fixed, but you can also change the tensions. And that's part of the study, is they want to see how does changing the tension affect the resistance. Also, shout out Jacqueline, our shop manager. She's been a huge help.
I was just wondering, because I feel like this is a very specific application. Was there anything online or any other machines that you could take inspiration from, or was it just Heatcon's old system that you had to kind of build off of?
It was just Heatcon's old system.
Oh.
Yeah, just one of one.
There's that one YouTube reel.
Yeah. There was one YouTube reel where someone wrapped duct tape around a rope. That's it.
It's like 5 seconds long.
Okay.
No, this is a real basic question for some of the juniors in the room. What would you like to tell yourself 9 months ago that you know now?
I got a few things, but I would say, I would say get started early. Like, put pressure on everybody. Don't be afraid to lean on anyone too. Just make sure that you're putting in as much work as you can, as early as you can. And I'd also say make sure that you're working with, you're making sure everyone's included, including your faculty advisor and even your sponsor liaisons, and making sure everyone's just in the loop of what's happening. And also be transparent. I feel like, considering how many different components there were, it was really difficult for us because it was 5 different components, so we're all split up, working on our own parts. So just doing progress checks and making sure we know how we want to integrate it all in the end, that would really help with making your final product and making it much faster too.
I think to add on to that, I've sort of learned the importance of having a good leader throughout it, because it's really important to make as many decisions early on as possible as you can, and really narrow your scope as soon as you can. I think, in hindsight, realizing how much of a challenge it was going to be for specifically the electrical components on this system, because that's a little bit outside of our field of expertise. Reaching out more early for that stuff would be good.
Maybe you already mentioned this, but you talked about the importance of controlling the tension. How accurately can you control the tension? Do you have some numbers that you can give, tolerances and stuff?
We do not have those numbers because there isn't any system on this to measure the tension. That is something that would probably be good to include in future work. Right now, the current idea is to just measure the resistance based on the tension, or based on the position of the linear actuator, essentially. From there, you might be able to, get a model out and calculate that. But it would also be nice to have some mechanism on that splicer to measure the tension.
Okay, let's thank the Econ team.
University Museum of Art.
Our museum uses a lot more energies than other buildings, so our task is to compile a list of optimization strategies to keep the artwork safe in the art storage and exhibition areas, and to keep the general public area very comfortable.
Following industry standards for heating and cooling in museums, we researched and calculated the ideal HVAC and lighting set points to achieve the most energy savings.
We used industry standard simulations of the building baseline for HVAC and lighting and created an hourly schedule with temperature set points modeled after the control strategies we chose and compared until we achieved maximum energy savings.
Anyways, with the simulation results, we used Excel to perform analysis and calculations to determine what factors give us the best energy savings. Join us on Project Day to learn more.
LiDAR and tracking camera systems are powerful but often rely on expensive proprietary hardware. Working with Metrola, our Seattle University design team built a cost-effective modular alternative. We started by designing a universal aluminum mounting bracket to hold commercial off-the-shelf sensors. This setup gives us industrial performance for a fraction of the traditional cost. To make the sensors work together, our software pipeline takes the real-time LiDAR point cloud and fixes it to detect specific targets like pedestrians. The system then instantly translates those 3D coordinates into precise pan, tilt, and zoom commands, keeping the subject perfectly in frame. Everything runs locally on an edge computer and a router, delivering a highly scalable and adaptable tracking solution.
Welcome to the metal-rich asteroid Psyche 16. It is located between Mars and Jupiter, approximately 300 million miles from Earth. Exploration of this asteroid has just begun, with an orbital projected to reach in 2029. Until then, scientists are not fully certain of what terrains are on the asteroid's surface. Back on Earth, a team of engineers is working hard, designing a rover suited for the potential terrain it might encounter. Sponsored by the NASA Psyche mission, the senior design team INT 26.4 present our rover design. Our is the traditional rocker bogie suspension system, controlled by a LiDAR operating system, powered by an 11-volt LiPo battery, all compiled in an acrylic housing.
Hey, is that Origami Robotics?
No, it's not. But you know what is?
Seattle University INT 26.5.
NASA Psyche mission, Origami Robotic Exploration Team.
Come to Project Day to learn about our research into origami robotics application for space exploration on asteroid Psyche. See you there.
What is up, everybody? We are Team INT 26.2. We're a team of mechanical and electrical engineers working with McKinstry on grid harmonizing the Seattle University Museum of Art.
But what is grid harmonization?
Glad you asked. Grid harmonization is the process of shedding or shifting building electricity demand to reduce stress on the electrical grid.
Grid harmonization techniques aren't usually applied to museums, since the galleries have strict environmental requirements to protect the condition of the art.
McKinstry tasked us with coming up with some ideas for grid harmonizing the building without compromising the integrity of the artwork. We came up with 3 ideas.
The strategies are battery energy storage system, phase change materials, and non-gallery load shedding.
If you're interested in hearing more about these unique and innovative strategies,
feel free to stop by our poster or our presentation and learn how we keep the grid and the gallery in harmony.
Oh man, what's the data center?
I've been hearing all this talk about data centers. I just wish there was a way for me to learn what it was.
What if we have a Lego version? Like we can just plug and play a mini version, a smaller data center.
Introducing Winter River, a modular data center training simulator. Built in partnership with Amazon Web Services and Seattle University. Every search, every stream, every message sent, all of it lives somewhere. Winter River. Learning starts here.
Hello, we are ECE 26.2 and our team is sponsored by Sound Transit. They are the regional public transportation agency in the Puget Sound area, serving millions of passengers across their various services. Our project focuses on their linked light rail. When a 3 or 4 car train pulls into a station, it will stop at the designated 4 car sign at the end of the platform. This ensures that tactile wayfinding paths on the platform floor perfectly line up with the second and third car doors, allowing passengers who are visually impaired to easily find their way onto the light rail. However, when a 2-car train enters and stops at the end of a station, one of these paths lead to a spot with no car, resulting in a safety hazard. Sound Transit has tasked our team with designing a lighted platform berthing marker that will illuminate when a 2-car train pulls into a station. This system must be able to reliably count the number of incoming cars and light up a sign if a 2-car train enters, indicating to operators where they should stop. This solution aims to uphold Sound Transit's mission of improving public transit for all passengers, ensuring high quality, safe, and inclusive transportation for everyone in the Puget Sound. We look forward to seeing you at Projects Day 2026.
Hi, we are Team Interdisciplinary 26.1, a mix of mechanical, electrical, and computer engineering students working alongside McKinstry to help optimize SUMA, aka the Seattle University Museum of Art.
Our museum uses a lot more energies than other buildings, so our task is to compile a list of optimization strategies to keep the artwork safe in the art storage and exhibition areas, and to keep the general public area very comfortable.
Following industry standards for heating and cooling museums, we researched and calculated the ideal HVAC and lighting set points to achieve the most energy savings.
We used industry standard simulations of the building baseline for HVAC and lighting and created an hourly schedule with temperature set points modeled after the control strategies we chose and compared until we achieved maximum energy savings.
Anyways, with the simulation results, we used Excel to perform analysis and calculations to determine what factors give us the best energy savings. Join us on Project Day to learn more.
LiDAR and tracking camera systems are powerful but often rely on expensive proprietary hardware. Working with Metrola, our Seattle University design team built a cost-effective modular alternative. We started by designing a universal aluminum mounting bracket to hold commercial off-the-shelf sensors. This setup gives us industrial performance for a fraction of the traditional cost. To make the sensors work together, our software pipeline takes the real-time LiDAR point cloud and fixes it to detect specific targets like pedestrians. The system then instantly translates those 3D coordinates into precise pan, tilt, and zoom commands, keeping the subject perfectly in frame. Everything runs locally on an edge computer and a router, delivering a highly scalable and adaptable tracking solution.
Welcome to the metal-rich asteroid Psyche 16. It is located between Mars and Jupiter, approximately 300 million miles from Earth. Exploration of this asteroid has just begun, with an orbital projected to reach in 2029. Until then, scientists are not fully certain of what terrains are on the asteroid's surface. Back on Earth, a team of engineers is working hard, designing a rover suited for the potential terrain it might encounter. Sponsored by the NASA Psyche mission, the senior design team INT 26.4 is proud to present our rover design. Our approach embraces the traditional rocker bogie suspension system, controlled by a LiDAR and Raspberry Pi operating system, powered by an 11-volt LiPo battery, all compiled in an acrylic housing.
Hey, is that Origami Robotics?
No, it's not. But you know what is?
Seattle University INT 26.5.
NASA Psyche mission, Origami Robotic Exploration Team.
Come to Project Day to learn about our research into origami robotics application for space exploration on asteroid Psyche. See you there.
What is up, everybody? We are Team INT 26.2. We're mechanical and electrical engineers working with McKinstry on grid harmonizing the Seattle University Museum of Art.
But what is grid harmonization?
Glad you asked. Grid harmonization is the process of shedding or shifting building electricity demand to reduce stress on the electrical grid.
Grid harmonization techniques aren't usually applied in museums, since the galleries have strict environmental requirements to protect the condition of the art.
McKinstry tasked us with coming up with some ideas for grid harmonizing the building without compromising the integrity of the artwork. We came up with 3 ideas.
The strategies are battery energy storage system, phase change materials, and non-gallery load shedding.
If you're interested in hearing more about these unique and innovative strategies, feel free to stop by our poster or our presentation and learn how we keep the grid and the gallery in harmony.
I've been hearing all this talk about data centers. I just wish there was a way for me to learn what it was.
What if we have a Lego version? Like we can just plug and play a mini version, a smaller data set.
Introducing Winter River, a modular data center training simulator. Built in partnership with Amazon Web Services and Seattle University. Every search, every stream, every message sent, all of it lives somewhere. Winter River. Learning starts here.
Hello, we are ECE 26.2 and our team is sponsored by Sound Transit. They are the regional public transportation agency in the Puget Sound area, serving millions of passengers across their various services. Our project focuses on their Link Light Rail. When a 3- or 4-car train pulls into a station, it will stop at the designated 4-car sign at the end of the platform. This ensures that tactile wayfinding paths on the platform floor perfectly line up with the 2nd and 3rd car doors, allowing passengers. However, when a 2-car train enters and stops at the end of a station, one of these paths lead to a spot with no car, resulting in a safety hazard. Sound Transit has tasked our team with designing a lighted platform berthing marker that will illuminate when a 2-car train pulls into a station. This system must be able to reliably count the number of incoming cars and light up a sign if a 2-car train enters, indicating to operators where they should stop. This solution aims to uphold Sound Transit's mission of improving public transit for all passengers, ensuring high quality, safe, and inclusive transportation for everyone in the Puget Sound. We look forward to seeing you at Project Day 2026.
Hi, we are Team Interdisciplinary 26.1, a mix of mechanical, electrical, and computer engineering students, working alongside McKinstry to help optimize SUMA, aka the Seattle University Museum of Art.
Our museum uses a lot more energies than other buildings, so our task is to compile a list of optimization strategies to keep the artwork safe in the art storage and exhibition areas, and to keep the general public area very comfortable.
Following industry standards for heating and cooling in museums, we researched and calculated the ideal HVAC and lighting set points to achieve the most energy savings.
We used industry standard simulations of the building baseline for HVAC and lighting and created an hourly schedule with temperature set points modeled after the control strategies we chose and compared until we achieved maximum energy savings.
Anyways, with the simulation results, we used Excel to perform analysis and calculations to determine what factors give us the best energy savings. Join us on Project Day to learn more.
But often rely on expensive proprietary hardware. Working with Metrola, our Seattle University design team built a cost-effective
This one is muted. Hello, everybody. Welcome to the last session of the presentations today. Just a reminder that right after this hour, there will be a poster session. And please go around, find our students who have with their posters, who are standing next to their posters, and you can get in depth of understanding and demonstration of what they have done. My name is Theodora Schumann. I'm a coordinator for mechanical engineering projects here at CLU. But this session also has electrical engineering projects. So we are combining efforts here in this session. I want to thank everybody who has come here to support our students, listen to them. And I want to thank especially our sponsors who are here, who have helped us and get these projects into reality. You know what? Don't be afraid and don't be shy to ask the students some tough questions when they're done. Yes. Yeah, exactly. So I'm going to, the floor here is to Dr. Shen Ren, who will be moderating this session.
Thank you, everyone. I'm Shen. 3 presentations, each one is 15 minutes. We'll roughly get 5 minutes Q&A. If it's too hard, I won't give you the microphone. And we have our first team from mechanical engineering and sponsored by the Xenops. Good luck.
Yeah, hello everyone. We are Mechanical Engineering Team 26.5, and we worked on a vibration damping pod mount for modular factory machines. I'm Ty Smith.
I'm Sarah Wolf.
I'm Hayden Alcorn.
I'm Samir Gill.
And I'm Jack Cloward.
Our faculty advisors were Dr. Gilbertson and Dr. Schumann out of the Mechanical Engineering Department, and our sponsors were Will Gibbs and Charles Lyford out of Xenops Manufacturing Technologies. So what is Xenops? Well, they are the factory. Currently, they build software packages that help engineers in every stage of factory development. Their goal is to help grow the manufacturing industry in the United States. Xenops wants to launch a new product line of small machine shops to enhance manufacturing work at their fabrication sites. This product consists of lines of modular pods and stands. Once at a site, these pods will be stacked on the stand, and contained within each pod is a small machine. This could be a 3D printer, a mill, or a lathe, and these machines will complete manufacturing tasks at the worksite as needed. Xenops tasked our team with creating a mount to connect these pods to the stand. A design challenge for this project was to damp vibrations from these machines as they operate. Unchecked vibration causes 3 things. First, noise. Vibrations radiate through the structure as audible sound. This can be harmful to those working in and around the machines. Second is wear. Repeated motion grinds down bearings, loosens fasteners, and degrades tooling. And third is resonance. At certain frequencies, vibration is amplified. A small oscillation in one pod can build into a force large enough to compromise the structure of the stand itself. The technical requirements put on our project was for our mount to support a maximum pod weight of 50 pounds. Max deflection was to be no more than 1/4 of an inch. This is to stop pods from hitting one another when stacked. And our final requirement was to reduce vibration transmission between the pod and the stand.
So, now that we've talked a little bit of our problem and our design requirements, let's dive into the beginning of our design process. Right off the bat, we noticed that we had 2 very contradicting requirements. We need to securely mount our pod to our stand while also reducing the vibrations. So, how do we do this? We were asked a bunch of questions in the beginning, 2 of which stood out to us. One was, why not bolt the pod straight to the stand? Or, why not use a soft rubber pad behind it to mitigate the vibrations? Let's explore that, and we'll see why these don't work. Do you mind hitting it for me? Yeah, thank you. So, first, we have our rigid mount. This would involve securing the pod directly to the stand. In other words, just bolting it straight on. This would solve our weight issue. It would hold the weight of the pod and our machine inside of it. But because the pod is directly mounted to the stand, the vibrations coming from the machine would translate directly to that stand, potentially harming other pods and other machines, and also cause a lot more wear, resonance, and a lot more noise than we want. So, we next explored the rubber pad. This is as you can see, is a rubber pad. The idea behind this is to mount it directly onto our stand. Oh, yeah, nice. Okay. So the idea was to mount it directly to our stand. First, we would mount the pod, or the rubber pad, sorry. Then we would mount the pod directly to the rubber pad. The only problem with this is that the rubber pad is soft, so the pod would deflect and sag underneath the load. So if you put a machine in it, it will fall down. This would hit against other pods along the array, causing a huge safety hazard, causing misalignment, causing machines to break, and we don't want that. So we then asked ourselves, how could we fulfill these two requirements into one design? Our team came up with 4 separate designs. First, we had a donut locking mechanism. Then, we also had a ball pin locking mechanism, a cam locking design, and then finally, our dovetail design. After a lot of deliberation and a lot of analysis between our team, we concluded that the dovetail design was going to be our best bet to fulfill all these requirements. And now, we'll show you why.
So before I tell you about our system, I first want to talk about what a dovetail is. A dovetail is a self-aligning joint. One of the main reasons we chose it is because it can hold the weight of the pod and it can lock it in place. Our dovetail consists of a female dovetail that will interlock with a male dovetail. And if we take a look at the front here, we can see that the female dovetail sits flush with the male dovetail. So now that we know what a dovetail is, let's go ahead and talk about our design. Before I tell you about how our system works, I want to go over some of the vocabulary of our components. So we'll start with the pod side. All right, here we can see that we have the male dovetails. These are the same ones that I showed you earlier. We also have the gearbox, which helps actuate and move our system. The gearbox contains a bidirectional screw. A bidirectional screw has one side that is right-hand threaded and the other side that is left-hand threaded. We also have the dampers, which help mitigate our vibration. Okay, so we'll take a look at the stand side. On the stand side, we have the female dovetails. These are also the same ones I showed you earlier. So now that we have some of the vocabulary, let's go ahead and talk about how someone would operate this. So how does our system work? So it starts at the front of the pod. There is a front axle that the user will use a drill to turn it. This will allow our gearbox to engage. So if we look at the other side, the male dovetails will come down and it'll end up looking something like this. Then the user can push the pod into the stand, like that. They will then turn the front axle the other direction. This will allow the male dovetails to come up and lock in place with the female dovetails. We take a closer look here, we can see that they are flush against each other, which allows it to mount. So I've just showed you the CAD model, and now I want to show you our physical prototype, so we'll have a video in the next slide. All right, here we can see the drill. It's turning the front axle one direction, and then the other side, we can see the male dovetails coming down. This is not sped up, so this is real time. It can go as fast as you want because the drill. All right, and then here we can see the pod is up against the stand, and we can see the male dovetails rising to meet with the female dovetails. All right, and then here we can see that they are locked in place, and the pod can fully sit mounted by itself. All right, so now that we've seen our model, let's go ahead and talk about some of our design details and why we chose some of our components and how we designed them.
Okay, focusing in on the specific details of our design, the gearbox and screw, a challenge we were faced with was we needed to torque and rotate a bidirectional screw in order to engage our mounting system as shown in the previous slides. Our solution was to match or pair the bidirectional screw with 2 matching threaded nuts, brass nuts, that when used together will create a locking mechanism that resists loosening from vibration. To rotate the bidirectional screw, we chose to use a worm gearbox, primarily due to its self-locking capability. A high friction between the worm and the wheel gear prevent the bidirectional screw from rotating the front axle. Another advantage is the orientation of the gearbox allows us to rotate the bidirectional screw directly from the front of the pod via the front axle.
The next design details that we want to go over is the dovetail geometry. The first major change we made to the dovetails is we had to make them thicker. These dovetails had to stay within that vertical guide rail that you can see, but it had to extend over that gearbox that Jack had just talked about, so it is the first and only point of contact between the pod and the stand. The second major change was adding an angle geometry where we added a 10-degree angle to that pod, to the dovetail. And this serves two major functions. The first major function being it fully locks the pod into place in all degrees of motion so that it cannot slip left or right laterally. We originally had a square dovetail that was flat, and the pod could move left or right due to those vibrations. The second major function of the angle geometry is allowing the pod to self-center itself as the user pushes the pod into place, as those kind of act as a guide rail that will move the pod there. The next and last design detail we want to go over is the dampers. The main goal of the dampers is to absorb the vibration before it reaches the backplate. We were able to achieve this by using a wire rope isolator, and we chose this due to the system's deflection requirements of a 1/4 inch. With these dampers, we were able to achieve a maximum deflection of 3/16 of an inch, so we were good there. And the second reason we chose these dampers is they're still able to move enough to absorb those vibrations, and they're not too stiff. So we were able to receive a average vibration reduction of 30%. Another component that we used was the locking washers. These washers were used at the bolt interfaces, and they were used to dig into the fasteners and ensure that the bolt does not vibrate out of place due to these vibrations. Next, we want to go over some project recommendations for any future team that is going to pick up this project. The first one we recommend would be adding a hard stop to the screw, as right now the mechanical resistance of the gearbox is currently the only part that is holding the pod up. A hard stop could further validate the safety of that mechanism. The second would be to conduct finite element analysis on the mount. We have run a lot of hand calculations and found that our minimum safety factor is well above 30. Running finite element analysis would help determine areas you could remove some of that material and cut back on costs. And the last recommendation we have would be to iterate on the damper design, as these dampers were mainly chosen to resist some of that deflection. There could be better dampers that are suited to fit other mechanisms in the pod. Lastly, we have some acknowledgments and people we'd like to thank. First, we'd like to thank our sponsor, Will Gibbs and Charles Lyford out of Xenops Manufacturing Technologies. We would also like to thank our advisors, Dr. Gilbertson and Dr. Schumann. Special thanks to our shop manager, Jacqueline Romelli, who's been a big help, and the Project Center staff as well. Thank you all.
Any questions?
Hi. First of all, great work on the presentation. During your design process, were there any problems or any hiccups that came along the way? And how did you guys solve that?
I would say the biggest problem that our group had was probably trying to find a damper that would actually work for the system. It's a 22-inch long pod, and you can only have a 1/4 inch of deflection. So to have a damper that is not only soft enough to allow the vibrations to get damped, but stiff enough to maintain that deflection, that was a really hard medium for us to find. Yeah.
All right. I had a question about beautiful dovetail design, by the way. I love the 3D models, love the decision. I had a question about, is there a particular reason why the dovetails were mounted like an equal sign instead of in like parallel with each other, if that makes sense? I don't know if you guys were ran through that possibility.
I think one of the benefits of having it is an equal sign, is that it can hold the weight with gravity. If it's parallel, then you'd have to put something under there to hold it, but that's also a really good point.
First of all, great presentation. Love the animations. Could you guys walk through your prototyping process? How did you start figuring out the materials that you wanted to use and stuff like that?
Well, first in the design process, we really wanted to think about how we could hold the weight, which is how we came up with the dovetails. And then we realized that we need the dovetails to move to allow the box to be pushed in. So that's how we came up with the gearbox. It helps actuate our system. For materials, we used aluminum because that's what we had available. And yeah.
Just kind of adding to that a little bit, the choices that were determined to our materials. It's just that we had a lot of cost constraints. We had a lot of for for example, like we couldn't like internationally ship, we couldn't like get cheaper options, so we had to like find ways to like cut down, find which materials to use, where we can like use the shop as well, and like just kind of like manage all that. So that's all like kind of factored into like what our final design looked like.
So for the dovetail mounts themselves, why did you choose the specific angle of 10 degrees?
We originally had it at a steeper angle, and we realized with 10 degrees, it helps the pod actually slide into place. If we went any steeper, it'd kind of catch or it'd like jump into place. The 10 degrees allowed for a pretty easy transition in that market. Yeah.
I don't know if this was in the scope of your project, but were there any considerations on external factors like a seismic zoning, depending on, for example, where this warehouse might be located and how that certification would apply to the stands themselves?
Could you repeat that question?
Yes. So ultimately, where these pods might be deployed, there are certain geographical seismic zones, right? And so those external, for example, earthquakes are going to create some additional forces required, not just for the attachment, but for the whole assembly. That might be isolated at the base. Was there any consideration, or was that just eliminated because the scope of the project was just how it attaches and not necessarily the entire base?
Yeah, I would say that that is a little beyond the scope of our project. We were just given the stand, and we were just working on the interface between the pod and the stand. We have not worked on the stand itself and its own vibration damping. But good question.
The last question.
I second what people said about it being a very articulate and clear presentation, so thanks for that. Presumably your pods are relatively heavy, especially made more so when they're loaded with equipment. Was there consideration given to the ergonomics and usability of the insertion in terms of keying, locating, visibility of the fixturing method, and then user feedback of when the fixturing is completely engaged?
Yeah, that's a really good question. When we went into this project, we didn't have any constraints of how many people needed to operate the machine. In the future, our sponsor did tell us that ideally a robot would be the one to mount the pod. So that was not something that we considered, but that is a really good question, especially if you have someone who is operating the machine. Did that answer your question? Okay.
Thank you.
Thank you, guys.
Who has the other clicker? Good job, good job. It's the best version that has it. Who has the other clicker?
Oh, I think I popped it.
That's why I'm looking for the. All right. Are you using a laptop?
Yeah, I'm using.
Okay, here. Just connecting this one. Don't worry about Zoom. And let's double check on your clicker before you go presentation. Let's try on here.
We only need one.
You only need one? Okay.
Where's the
sure.
dongle for it?
I think this one's better.
Oh, the dongle's already in.
Yeah. Dongle's already in here. So just try that if that works. Give it a try. That works. Okay, perfect. Okay.
Then we'll take
one over there, one here. Who's going to speak first?
Testing.
You're going to speak first. I'll introduce you and then you can have it.
Yeah. Testing.
Oh, here. Okay, let me try to fix it. And this is the one to go?
Don't you have a? I only have one USB-C, so I can go like this.
Wait a minute. That's okay. Okay. Yeah, you got another one here.
Wait. And then it's
and then USB-C here.
USB-C here to put it on. Yeah, that should work.
Okay.
And then,
Do you need any more?
yeah, no, we only need one.
It's still another. Oh, okay. It just loaded. Do you want to try it one more time? Just want to make sure. Perfect. All right. The next two presentations, both of them are from the interdisciplinary team between mechanical engineering, electrical engineering, and both projects come from the McKinstry. The first one.
Oh, hello everyone. We are team INT 26.1, Seattle University Control Optimization Study.
Hello, my name is Kian Alberghini. I'm a mechanical engineering student.
Hello, I'm Rowan Jorgensen. I'm also a mechanical engineering student.
I'm Tung Nguyen. I'm a computer engineering student.
I'm Andrew Tu, an electrical engineering student. Our final member is Nuria Tamam, who is a computer engineering student. Unfortunately, she was not able to join us today, but we would like to thank her for her contributions to our 1-minute promotional video.
And our liaison engineer is Taylor Alzingo Sagado. She's a professional engineer at McKinstry. And our faculty advisor is Kirk McLansbury. He's also a PE, but at Doman Energy. And about our sponsor, McKinstry, they would be working as the mechanical, electrical, and plumbing contractor for the project. Speaking of project, our project, also known as SUMA, you can see a render right here about how it potentially look like. SUMA actually have a quite interesting background to it. It all started with the donations from the real estate developer Richard Hedren in honor of his late wife Elizabeth. He donated an art collections valued at around $300 million, as well as $25 million in construction seed money. The SUMA will be replacing the Lee Center for the Arts. It will be operated entirely on electric power, and it will serve as both an art galleries as well as a learning area for the students. So why our projects? Well, according to our findings, HVAC and lighting takes up more than half of the energy usage in US commercial buildings. Museum uses even more energies because they need 24/7 monitoring and modulations of temperature and humidities. SUMA is no exception. And we'll be working to reduce that energy usage by modeling the energy with the software ISVE. We will be working with the LEED certification. It is a very well-recognized green building certifications. It basically measures how sustainable your building is, and we'll be aiming for the LEED Gold certifications, which is between 60 and 79 points. Our focus will be on the optimized energy performance credit, which can earn us a potential of 18 points towards the goal. And here is the proposed layout for SUMA. There are different areas such as the art galleries and as well as more general areas such as the classroom, the cafe, and the lobby. The art galleries are very strict in terms of their temperature and humidity regulations, while the general areas are more relaxed. And you will see that most of our gain in energy reduction will be in the general areas. And here's our the budget for our project. We would also be working with external constraints, such as on the codes and standards from both Seattle and ASHRAE.
So we're going to start with our HVAC optimizations. So this is our baseline model provided by McKinstry, and it shows the energy use specifically for HVAC systems over the year, month by month. We use this model to test each controls optimization strategy individually and then compile them at the end. And our baseline HVAC electricity use was over 207,000 kilowatt hours per year, which equates to around $29,000 with a 14-cent kilowatt hour conversion.
For night setback, we tested both widening and narrowing the bands allowed during the unoccupied times of the building.
In general, night setback is the rollback of HVAC systems overnight when the building is unoccupied. So we tested different temperature bands, as Caden will continue with.
For that, we tested widening and narrowing the bands that is allowed during unoccupied hours. We tested the wider bands, and this resulted in a reduction of energy usage. We followed this until we saw a point of diminishing returns, and that was at 55 degrees, where the heating would turn on, and at 90 degrees, where the cooling would turn on. And that resulted in a 2,600 kilowatt hour reduction, or about 1.2% energy savings.
Our next optimization strategy is optimal start. This is calculating the time needed for the HVAC systems to get the building back up to our occupied temperatures required. If we started this too early, then it would be a waste of energy, but we still have to have it on time so that the guest comfort with those occupied temperatures is maintained.
For optimal start, with our temperate climate here, we tested reducing this allotted time for the building to heat up. This reduced the energy usage, so we chased this until we saw a point of diminishing returns. Then we backed it off slightly so that we could, because this is a very simplified and it's a model, and this when it runs into reality, sometimes those systems takes a little longer to get the building to temperature. And so we backed it off to 0.3 hours, and this resulted in a 11,000 kilowatt hour reduction in energy usage, which is about 5.2% energy savings.
Then we tested supply air temperature adjustment. This is the temperature of the cold deck and hot deck air that is mixed to cool and heat the building. One thing to note here is that this is the only strategy that would apply to the zones that hold art because of the strict temperature and humidity requirements in those zones.
For supply air temp, we tested more and less extreme values. These values with higher delta T or difference in temperature resulted in more energy savings. So we chased this until we ran up against the ASHRAE 55 guidelines. So we settled at 50 degrees of cold air supply and 95 degrees of hot air supply. These would be then mixed in a variable air volume damper that would be then put into the room. So you won't be blasted with 95-degree air. This resulted in a 10,000 kilowatt hour reduction in energy usage, which is about 4.7% energy savings.
Now we have scheduled start. This is creating that schedule of occupied time based on when the building will actually be occupied. So in general, this would be when the art museum would open, but we wanted to investigate further optimization for the classroom spaces by adhering to specifically the class time schedule shown here. So to do that, we created one simulation that was fully unoccupied and one that was normally occupied, and combined them using an 8760 profile, which is an hourly profile across the whole year.
For scheduled start, this allowed us to classify the building as unoccupied for a lot longer, meaning we no longer have to take in outside air to condition. And since we don't have to condition that outside air, that saves energy. This is per ASHRAE 62.1. And with that, that resulted in a whopping 88,000 kilowatt hour reduction, or 42.5% energy savings.
Lastly, we have the occupied air temperature adjustments. We wanted to test expanding this band of just what temperature we allowed it to be inside of indoors in these zones, and we wanted to balance that with guest comfort.
For occupied air temp, we tested a multitude of values in different bands. We tested 5, 10, 15 degree bands. We even tested a floating band, which would take monthly energy usage data between different set points and choose the lowest out of that to create a dynamic set point. However, we had to make concessions to guest comfort. So we chose a moderate comfort level, which was about 67 at the lowest end to 76 at the highest end. This resulted in a 21,000 kilowatt hour energy reduction, or about 10.3% energy savings. Now we combined all of the aforementioned strategies into one high fidelity model. And when that was run, which took about half an hour for that one simulation, it used about 130,000 kilowatt hours of energy. And that is a combined savings of about 78,000 kilowatt hours from the baseline. And that is, as a percentage, is about 37.4%.
Moving on to the lighting controls optimizations, we ran a simulation of the McKinstry baseline model that we were given, and we looked at the lighting loads for the entire system, which came out to 55,300 kilowatt hours for the entire year. Using a conversion rate of 14 cents per kilowatt hour, we get $7,700 per year. So our first optimization is daylight harvesting, which dims artificial lighting in response to available daylight. We are given a default ramp function in IESVE, and we optimize this ramp function so that at 5-foot candles or less, the lights go up to 80%, and at 80-foot candles or more, the lights turn off. And using the optimized ramp function, we get the monthly total shown in the graph there. And this results in about 3.8% in energy savings, or a 2,100 kilowatt hour reduction from the lighting baseline. The next is high-end trim, which lowers the user's maximum lighting output. And just as an example, if we lower the user's maximum output to 80% of what the lights can actually output, this will prevent overlighting the rooms and save on electricity. However, we still do want to make sure that the rooms are adequately lit, so we did foot candle calculations for each room, and we ensured that each of the foot candles for each room was greater than the foot candle recommendations from the Illuminating Engineering Society. To simulate high-end trim in IESVE, we would have to lower the lighting power density, and to meet the Seattle Energy Code, the lighting power density would have to be lowered by at least 15%. So from this, we found that high-end trim was applicable in classrooms, dining areas, food preparation areas, the lobby, restrooms, and stairways. And lowering the lighting power density in applicable areas, we get the monthly total on the graph there. And this totals to about a 9.6% energy savings, or a reduction of 5,300 kilowatt hours from the lighting baseline. Our last lighting control strategies is time switch controls, which turns the lights on and off based off of a custom 8760 schedule. We created 5 distinct schedules for 5 distinct zones, and for each of these schedules, we changed the modulating value, which was the light output as a percentage. And while creating these schedules, we took into consideration class schedules, business hours, holidays, and school breaks. So implementing all 5 of these schedules, we get the monthly total output as a graph. And this resulted in about a 24% energy savings, or 13,100 kilowatt hour reduction from the lighting baseline. Combining all of the aforementioned lighting strategies, we see that SUMO will use 38,000 kilowatt hours, and this equates to about 17,400 kilowatt hour reduction from the baseline, or a 32% reduction. And combining all of the HVAC strategies and the lighting strategies, we see a 21% reduction from the baseline, and we'll save about $12,500 per year. Going on to lead points, the McKinstry baseline that we were given gained 2 points under lead V4 and 6 points under lead V4.1. Our model gained 6 points under lead V4 and 10 points under lead V4.1.
As with all projects, there were challenges, one of which being having to familiarize ourselves with the Seattle code as well as the ASHRAE code. We were also learning the ISVE software. It was quite a complicated software. We were also working with a very dynamically changing model, and which means that we had to adapt because we were working alongside McKinstry as they developed the model. Had we had more times, we would spend a lot more effort. Actually, we would reduce the set size so that we can really pinpoint that point of optimizations to really squeeze out those last few percentage of energy saving. And our suggestion for any teams that might pick up our projects is to look into fans. Those would increase the comfort for the guests, and as well as other weather-based strategies such as automatic shade, which would shield on the general areas from the sun. And we would also like to acknowledge all the lovely people at McKinstry, all our faculties at Seattle University, as well as the staff of the Project Center, the staff and animals of the Project Center. All right, thank you.
questions?
In your models, it looks like you modeled the HVAC heat loads and the lighting separately. Was there any interaction, or did you look at any interaction between the additional heat, which granted with LED lighting isn't going to be a lot, but could be some additional heat created by the lighting or lack of heat created by turning the lighting off on your heating and cooling models?
We initially did all of the simulations separately so that we wouldn't have any bleed over effects, so that we could look at the data trends on our own, and then they were combined into the final model.
Question back here. Again, I'm not just going to do it to the first group, so I'll get the second group here too. When you think of the factors that are unknown and, let's just say, potentially predictable in the future, say, for example, weather or occupancy, and you also consider what potentially, in terms of putting those algorithms into AI, what would be the sort of benefit of an AI-type induced control system, and how do you think that would help your project? Like, what were those factors that you said, you know, if I could only know or predict what I think would happen in this building, what were those type of factors that you could build into an algorithm?
That is a great question. We were looking at that at the beginning of a project. ISVE actually provide a Python interface to run all that AI stuff. We were using PyGrad at some point, but it turned out that it didn't quite work. We couldn't quite figure out how the Python interface worked, but our plan was to incorporate the weather data as well as maybe like a more detailed class schedule, and feed that into some sort of AI algorithm to spit out a more optimized control strategies than we can do manually.
Next question here.
When you're testing out the supply air temperatures with the different extremes, were the extremes based on just regular weather data, or was it specific to the annual weather temperature in Seattle?
This was based on a Seattle weather profile at, I believe it's Boeing Field, that was provided by McKinstry.
Any other questions? Thank you. Oh, here, okay.
And then dongles here as well. Oh, perfect.
Nice.
They can't get me.
We gotta go on. You got it. Okay.
He's starting it, and then
I'm talking.
But I'll say my name first, so that's why.
Okay.
I'll say my name. I'll give it to Max.
Hello. 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 Hello.
Hello. Hello. Hello. Do you hear my voice? Hello. Hello.
People over there should use the clicker, yeah? Oh, yeah, you guys should have the clicker. We can use the laptop. You guys should have the clicker. Yeah, whoever's standing over there.
Melvin has a clicker.
Oh, then we can use one.
Oh, okay.
You need the clicker now. For now.
Oh, yeah, you need to go first. Well, but he's going to talk first.
Oh, okay, I'll go. Wait.
You come here. For now, we can all stand like in line because we're just starting it. Hello.
Hello. Okay.
All right, last presentation for the day. Also from the McKinstry, we have another interdisciplinary team between ECE and mechanical. Here you go.
Hello, everybody. We are team INT 26.2,
working with McKinstry towards the grid harmonization of the upcoming Seattle University Museum of Art. My name is Melvin. I'm an electrical engineer.
I'm Ismail, electrical engineer.
I'm Ben, mechanical engineer.
I'm Max, mechanical engineer.
I'm Sam, mechanical engineer.
Our faculty advisor is the birthday boy, Mr. Shen Ren himself. And our industry liaison is Peter Alsbach.
Our sponsor, McKinstry, is a well-renowned multi-billion-dollar consulting, design, and construction company with the vision of working together, building a thriving planet. For the past 60 years, their mission has been to make the built environment healthier, more efficient, and safer through engineering expertise, construction excellence, and innovative facility operations spanning across the U.S. McKinstry has tasked us with developing efficient energy management strategies for the Seattle University Museum of Art's electrical and HVAC systems, allowing for successful grid harmonization without sacrificing operational performance, art integrity, or occupant comfort. The Seattle University Museum of Art is a 37,000 square foot art museum in development that will be located at 12th and Marion. The building's HVAC consists of two systems, one supplying the gallery and art spaces, and the other supplying the rest of the building. On behalf of protecting the artwork, our strategies cannot have major impacts on the architecture or interfere with the gallery HVAC systems. Grid harmonization is a way for buildings to optimize energy usage, reduce peak electrical demand, and enhance grid stability. The main way of participating in grid harmonization is through load shifting. During peak hours, when the grid usage is high and the grid becomes stressed, buildings can shift the time of which they consume electricity, reducing grid demand during those peak hours. The challenge with that being is that our museums are not typically designed for grid harmonization due to stringent environmental requirements such as temperature, relative humidity, and to protect the artwork in addition to occupancy comfort. This project looked to find innovative strategies to support a stable and interactive grid for the museum while following Seattle U's dedication to sustainability. Our metric for success applied to each strategy is a 10% annual on-peak load reduction.
This is going to be a figure that we'll be coming back to throughout the course of this presentation, just so we can kind of evaluate how successful our strategies are at meeting that reduction metric that Sam just mentioned. The dark blue line represents the electricity consumption of the building during the most heating-intensive day of our simulated year. You can see the electricity use spike up early in the mornings as the building comes online for the first time, and slowly taper off later into the night as the building closes. This dashed red line is our calculated grid demand limit. Now this is set at around 106 kilowatts, and it's derived from a LEED grid harmonization formula, which basically tells us the maximum allowable amount of electricity that the building can consume for us to have successfully qualified for that reduction metric. As you can see, there's a decent chunk of the day where the building's electrical needs are above that limit, so all of our strategies are targeted at closing the gap between those two lines.
So we initially brainstormed multiple strategies to achieve grid harmonization, such as compressed state energy, thermal energy storage, and geothermal energy storage.
After applying select criteria such as potential system costs, sizing, and complexity into a decision matrix, we managed to narrow that down into 3 strategies that we wanted to focus in on moving forward with the rest of our project. Those 3 strategies are non-essential load shedding, installing phase change materials, and integrating a battery energy storage system.
The non-essential load shedding team decided to focus on pre-cooling and preheating strategies within the non-gallery spaces within SUMA. Due to time constraints, we will only be presenting on preheating right now. In the winter, lots of electricity tends to go towards heating buildings. This is due to the fact that the outside is cold, but we'd like the inside to be at a nice temperature for when occupants arrive. So before occupants arrive during the winter, what we can do is we can turn up the thermostat. And this should have the effect of using more electricity demand earlier and less electricity demand during the typical peak demand period. And that should de-stress the grid during that later period of time. So this is a graph of the air temperature of a preheated office space within the SUMA building. As we can see in the preheating period, shown in red, the air temperature climbs up. And then since the air temperature is hotter than normal, what we can do is we can afford to turn the thermostat down during the typical peak electricity demand period, as shown in blue. And you can see that that temperature climbs down during that period of time. Now, moving on to the heating system's electricity demand, we can see that during the preheating period corresponded to more electricity demand, as seen by the red graph superseding the dark blue nominal curve. And then we can see during the typical peak electricity demand period, we can see that the red graph is now under that blue graph, meaning that we successfully shifted load and de-stressed the grid.
We'll now go on to discuss the implementation of phase change materials, or PCMs. Phase change materials are materials that have a very high latent heat capacity. This means that as they melt or freeze, they're able to absorb or reject an incredible amount of heat energy without changing temperature. In buildings, this allows them to act as sort of thermal sponges, absorbing excess heat energy while maintaining consistent temperature conditions. The graph to your right compares the internal temperatures of a building without phase change material implemented and a building with phase change material implemented. As outdoor air temperature changes, the PCM integrated building is much more effective at curbing these temperature fluctuations. This has the ability to reduce strain on HVAC infrastructure, which can lower building energy usage. Because the HVAC systems in the gallery space make up the largest proportion of energy usage in the building, we chose to implement the PCMs here. However, this does come with its own set of constraints. There are internal partitions that must be avoided, and the occupant's view of the artwork cannot be obstructed. The area available for implementation is shown in green. Because of this limited space, we chose to implement in the form of hanging baffles on the periphery of the space, and these will be located roughly here. The phase change material itself will be contained in these baffles, and as the temperature in the gallery raises, that material will melt, absorbing heat, and as it lowers, that phase change material will freeze, rejecting heat, lowering the strain on the HVAC systems. Along with this, we have a proposed control strategy of limiting HVAC capacity to 50%, and this will be from 7 to 10 in winter months, and from 12 to 3 in the summer months, and these times coincide with peak grid stress hours. Now, in order for the strategy to be valid, we must maintain those stringent gallery temperature requirements. As a reminder, this is 70 degrees plus or minus 2 degrees Fahrenheit, shown in this green section. Without any PCMs integrated during that 50% reduction period, the temperature falls out of this range, meaning that the artwork is compromised. With PCMs integrated, this temperature is maintained, protecting the artwork. To validate the amount of load we're able to shift, we can compare to our load limit from earlier. Now, this strategy does peak over this limit, but is still very effective at shifting load during high stress days when non-PCM HVAC is unable to do so.
So now we will talk about the battery energy storage system. The diagram shows the proposed battery energy storage system connection using 9 batteries in series. A series connection was chosen because it provides higher DC voltage while reducing the current and cable losses, making the system more efficient. We have 2 circuit breakers that protects the batteries and the building, and a bidirectional inverter that converts direct current to alternating current when the battery is discharging, and alternating current to direct current when the battery is charging. The final system design provides 125 kilowatt of power and total energy capacity of approximately 3,000 kilowatt hours. The image on the left shows the map of the museum's parking lot based on the battery's dimension and safety cage. Approximately 6 parking spaces are allocated for the battery system while applying the required required safety clearance and code consideration for battery energy storage systems.
Now, with that battery system in place, how do we decide kind of when and how it acts? To do this, we modeled a predictive control algorithm within Excel that runs through a kind of 3-step cycle every single day. At the beginning of every day, the control strategy will try to predict the electricity use of the day ahead. This is done utilizing all the past week's worth of electrical consumption data, as well as forecasted weather demand patterns. Using all of that information, it will then set a daily internal demand limit for itself, which is basically a ceiling capping off how much electricity that the building is allowed to pull from the electrical grid for that day. With that limit in place, the battery will then charge and discharge accordingly, ensuring that the building's electrical draw from the power grid remains below that internal limit. When applied to that figure that we've been kind of going back and forth with, just a reminder, here's that normal electricity use as well as the limit that we set for ourselves. For this specific day, our predictive control logic set an internal limit of around 88 kilowatts, and you can see that reflected in how the battery is charged and discharged. Early in the morning, the battery will charge up until at capacity, and then during periods where the building's electricity consumption goes above that limit that it's set for itself, the battery will discharge. Later on into the night, the battery begins charging again, recuperating all of that used electricity. Another thing that McKinstry wanted the battery team to look at is the potential carbon impact of implementing a battery energy storage system. Seattle City Light's average carbon emissions are usually relatively low due to their largely hydroelectric generation capacity. However, the concept of grid harmonization looks at a different metric, something called marginal grid emissions, which is what's represented on this graph here. Essentially, during hours when the electrical grid is stressed, during those peak load hours, Seattle City Light's hydro capacity is already maxed out at serving existing electrical demand. They can't just generate more electricity off a whim using hydro capacity. Therefore, any new electrical needs that come online during this time, think people getting home, turning on their lights, using their microwaves, turning on their TVs, that electricity need is met from Seattle City Light purchasing it from regional power plants, which typically burn fossil fuels, generating a lot more carbon emissions. This is represented in this pronounced spike later into the evening, which is something that grid harmonization can help to alleviate. One thing that McKinstry was curious about was, with the battery infrastructure that we've been going over for the past few slides, instead of that predictive control logic that we went over, what if we instead charged and deployed the battery according to this behavior, charging when grid emissions are low and discharging when high, and seeing if that could possibly significantly reduce or maybe even completely offset the carbon costs that come with installing a battery system.
So after that, we performed the life cycle analysis on the battery. Life cycle analysis looks at entire lifespan of the battery from manufacturing, transportation, operation, end of life recycling, and counts the carbon produced. The high carbon produced value is mainly because of the battery's manufacturing processes, which includes raw material mining, processing, and transportation to manufacturing facilities, which are all highly carbon intensive processes. We compare that value with the carbon reduced through using the battery for carbon reduction instead of grid harmonization. And we can see while the strategy significantly reduces carbon emissions, it does not totally offset the carbon produced by the battery's entire lifespan.
Through our results and analyses, we have 3 final recommendations to McKinstry. These are a supplementary approach, an innovative approach, and a practical approach. Our supplementary approach is our non-essential load shedding strategy, providing a benefit to the building at no additional cost. Our innovative approach is our phase change material strategy, offering an innovative method of shifting load on high grid stress days. And our practical approach is our battery energy storage system, offering a consistent year-round approach to grid harmonization. We'll now talk about some of the future recommendations we have for McKinstry to further the work in this project.
The non-essential load shedding team would like to see an improvement to the model so we can accurately represent the spaces inside of SUMA. This can help optimize the pre-cooling method mentioned before. We'd also like to integrate with other strategies to provide an additional layer of load shedding.
For the PCM strategy, we'd love to see McKinstry implement the addition of non-passive components such as fans, as well as implementing the phase change material in non-gallery spaces.
And for the battery energy storage system, we were curious about potential integration of generation capacity connecting to PV arrays on the roof of the art museum, also a more automated, responsive, real-time prediction control algorithm. Although one of the biggest things we wanted to look at is potentially optimizing the sizing of the battery. That insanely high carbon cost earlier was due to us needing to drastically oversize the battery to meet the requirements of grid harmonization. But if we instead size our battery around reducing SUMA's carbon contributions, we'd like to see if that could significantly reduce the amount of carbon produced when integrating this battery system. acknowledgements, we'd like to thank all the lovely people at Seattle University, the operations and maintenance team for giving us a tour of the utility facilities, as well as the project center, the engineers over at Kaufman and McKinstry for providing us with a lot of guidance on some perhaps unfamiliar topics, teaching us a lot about this topic, the Henry Art Museum for, again, giving us a facilities tour, showing us how they manage their energy systems, and WattTime providing us with carbon emissions data that we could use to investigate carbon impact of our strategies. Thank you.
Questions?
Your initial ideas, there were like 10 of them, and you guys reduced it down to 3. How did you go through the ideas that you had and figure out which ones would actually like make sense in the building? Did McKinstry provide any data on what they wanted, or did you guys have like full control to decide what would be like an option to do and what would actually like work?
Yes, that was actually one of the really exciting parts of this project starting off. They basically said, look and investigate whatever you want and see how effective it would be. So what we did was we tried to go through an exhaustive list of technologies covering a bunch of different like spectrums from thermal storage, electrical storage, thermal generation. And with that in mind, we applied the same kind of process for evaluating each of those, looking at potential sizing of existing systems that resemble it, potential costs, and also how complex and how many points of error for each of these systems there would be. We applied that all into a giant decision matrix, and then we kind of evaluated everything according to how it rated in each category, from like cost, complexity, size, weight, and that led us down to the final 3 options that we believe we could best represent through the work that we've done with IES.
Could you guys possibly go back to slide 27? There's a graph I had a question about. I'm like, Schumann, get me on that slide.
We have the numbers, that's good. We have the numbers on the side. We shouldn't.
It shows like your battery performance as compared to the.
The one, yeah.
Yeah. Is there a particular reason why 88 is the value? I might have missed it in terms of like the reasoning as to why that number was selected or why it had to be that way, but could you maybe explain to me why it's 88 in terms of why, if the limit's 106, would you not pick 105 or something?
Yes, that's the kind of concept underlying a big part of this battery sizing stuff. That isn't a value that we came up with. It's a value that our control algorithm kind of came out with, utilizing a mix of weighted averages the past week's electrical demand as well as potential temperature stress. The reason we didn't just set it to 106 for the entire year is when we were modeling this system, we had to model it as if it was actually in practice in real time. We only know that 106 value because we have the benefit of hindsight. We can kind of look at the system and see, oh, this is the maximum electrical demand. We break it down and come up with that 106 value. Typically, if your system is in place, you don't know exactly what it's going to be for that year. So we try to tune our control logic so it would set predictions in place every day and have the result kind of be under, just happen to be under that 106 limit.
Next question here.
Yeah, I just wanted to ask a little bit about the data and testing the space for all the excess heat that comes in. Did you account for attendance and the body heat that shows up, or is that just really not a part of the scale because maybe it's not as intensive of a heating component?
Yeah, we did account for that. Actually, that's one of the modifications we'd like to make to the model. Specifically, pre-cooling kind of didn't shift as much load because there were a ton of people modeled within the space. So at certain times, it would heat up the building, and there wouldn't be enough time to actually turn the thermostat up because the temperature would rise so fast. So yeah, we would like to model actually less people in the building, make it more realistic. Yep.
Hi, great presentation, y'all. I know that BESS systems can, or those battery systems can get kind of loud. I was wondering if you had to take into account any noise constraints with it being next to a museum or what that looks like.
That is a very good question. That is not something that we took into account when it came to designing the system. We weren't really too worried. We didn't think too hard. In hindsight, we might have wanted to, but we didn't think too hard about those excess like byproducts of generation like noise, purely because it's in the middle of a parking lot and it's right next to a bar. So we were kind of internally counting on the people on the weekends kind of covering up all of that noise, but in hindsight, fleshing the strategy out, taking that into account, and like the behavior of the surrounding environment would definitely be a good idea. So thank you.
Thank you. That's all of our presentations today. Thank you all again for all of the sponsors for the opportunities, and thank you all for continuing supporting our students. We still have the poster session up there, and we're looking forward to see you in the Project Day 2027. Thank you all.
The modular alternatives. We started by designing a universal aluminum mounted.
Thank you. All right. Yeah. Go take the pictures there. This is
In bracket to hold commercial off-the-shelf sensors.
Join us.
This setup gives us industrial performance for a fraction of the traditional cost. To make the sensors work together, our software pipeline takes the real-time LiDAR point cloud and fixes it to detect specific targets like pedestrians. The system then instantly translates those 3D coordinates into precise pan, tilt, and zoom commands, keeping the subject perfectly in frame. Everything runs locally on an edge computer and a router, delivering a highly scalable and adaptable tracking solution.
Welcome to the metal-rich asteroid Psyche 16. It is located between Mars and Jupiter, approximately 300 million miles from Earth. Exploration of this asteroid has just begun, with an orbital projected to reach in 2029. Until then, scientists are not fully certain of what terrains are on the asteroid's surface. Back on Earth, a team of engineers is working hard, designing a rover suited for the potential terrain it might encounter. Sponsored by the NASA Psyche mission, the senior design team INT 26.4 is proud to present our rover design. Our approach embraces the traditional rocker bogie suspension system, controlled by a LiDAR and Raspberry Pi operating system, powered by an 11-volt LiPo battery, all compiled in an acrylic housing.
Hey, is that Origami Robotics?
No, it's not. But you know what is?
Seattle University INT 26.5?